So check if he's still there. All right, so good morning, everybody, and welcome to the second day of our Dream Chemistry Award 2021. I wanted to say competition, but I don't want to say competition. I want to say fiesta. And yesterday we had the day of joy and maybe a bit of competing. Today it's going to be like pure joy. So I hope we'll enjoy ourselves, and it will be a celebration of science, and that's why we're here. So I'm very happy that you're here in vivo, but I also welcome everybody who's here online connected. And before I get to the first point that we have on the agenda, and that's actually awarding the top 5, who are 6, as you all know, and the winner of the Dream Chemistry Award 2021, there's space for me for thanks, and I really want to use this space. So, and I hope I will not forget too many people. Because this event would not be possible without a team that worked together, and also without really great support we got from this institute. So the first, I want to thank Zdeněk for making this possible, for hosting us, and yeah, thank you very much. This is great. And you know, I hope it's been great that you've been hosting it. It's the third time. Actually, you're hosting it here. And next time there will be a new director, so I hope the legacy will be passed to the new director.
The best days are over.
I'm younger. I would say the best days are still in front of us. But yeah, that's the only thing we disagree on. But I also need to mention, and I want to mention also Martin Fusek. We have a spin-off company, CEITEC, and that's actually through this company, we are funding this event and the prizes, because that's the way we can sponsor things through money that's from private sources, and it's much easier. So I'm really grateful to Martin, and I don't know if he's somewhere, but please tell him when you see him. We're very grateful that the CEITEC is supporting this event. So your travel, the prices, that has been paid actually through the royalties of the licensing fees we got from the drugs that were developed in this institute. So science is not only fun, not only beautiful, but sometimes can even bring money. Yeah, it happens. And yeah, we were lucky that it happened. And the team of people who really made this happen, who worked their butts off and bones off. So Dusan, the guy in between the real space and the virtual space, who's always telling me like, yes, you can. He's there, he's waving. Thank you, Dusan. Olda, whom I call Patrick or Andre for some reason, but it is Olda, and he did the interviews with you. Thank you, and he's there. And Tomáš. I mean, this is going to be horrible. I don't want to go to your office anymore. And Tomáš, the official photographer, the artist of the whole event, thank you very much. Also, the glass studio that actually made the award this year, and you only see like a 2D projection, but that's actually a small-scale version. The real thing is much bigger, so it's there. So yeah, you will see it pretty soon. So I'm very grateful to them. I think they did an awesome job. So that's my thanks, and I think we should get to the prizes. So the first prize I want to award, and I didn't consult it with anybody. It's my personal prize. So the bad news is it's not very valuable, but the good news is it goes from the bottom of my heart, and it goes to Bara, because Bara is the key person here. She really did everything. As you know, without Bara, nothing happens at Dream Chemistry Award, in Prague at least. Thank you, Bara. Okay, and now to let me announce the winners of the top 5 of the Dream Chemistry Award 2021. So the first of the 6 top 5s is Ghislaine Vantom. And Ghislaine, I hope you are online with us, and congratulations to your Happy Family event. Congratulations to making it to the top 5. The check will come. Here's the diploma. It will be also sent to you, and yeah, we look forward to see you maybe next year And all good luck with your new family situation. So that's Ghislaine. Maybe I should have said that. So making it to the top 5, I mean, you not only get this beautiful diploma suitable for framing, so, you know, put it in your office on a distinguished place so that every visitor sees it and you see it every day when you come to your office. But there's also like a small financial bonus of 1,000 euros that you don't have to display anywhere. It's totally up to your discretion what you do with it. Then we go in the alphabetic order, as is the custom in Dream Chemistry Awards. So the first of the top 5 who actually made it to Prague is Ahmed Badran. So Ahmed, please, come here. Congratulations. There we go. Okay. Robert, will you help me?
Sure. Ahmed, congratulations.
Yeah, and give him this. Yeah. Because Robert is really my partner in crime.
Yeah,
we are twin brothers. Yeah.
Right.
He's my younger brother, and he will be doing the event next year in Poland. So I'm looking forward. And I'm trying to treat him nice so that he invites me to Warsaw next year.
Okay.
Good.
Maybe next time you should unify your hairstyle somehow.
Start working on it. Yeah. All right. The second in alphabetic order who made it to the top 5 to Prague is Johannes Bintinger. So Johannes, please. Congratulations. Here is the one for you. The third one alphabetically is Luka Dordevic. Luka, please come here. Congratulations. Here is your diploma. And Robert will give you this. You see how, since Barry is not here, it's all a mess, but
It's nice. We
yeah.
nice to collaborate.
Yeah.
You know?
Right. Then comes Jarad Mason, alphabetically. Jarad. Congratulations. Great pleasure. And finally, we have Giulio Ragazon. Please. Come here. Congratulations. Okay. So, these are the winners. The 6 winners of the top 5. This is already a hairy joke, right? So, I won't say it anymore. Probably next year we'll have 5 from the top 5. But that depends on you. All right, what do we do now? Maybe it's time to say that we did in the end.
But do you know the winner? I don't.
Okay, Bara knows. But before I announce the winner, let me say one thing. So we had and this will sound like a cliche, like a complete cliche, but it's true. It was very difficult to decide because you were all great. And the proof that it was difficult to decide is that the deliberation of the committee took a good part of the afternoon between the end of your presentations and the dinner. We did make it all to dinner, so we didn't overdo it, but it was a long deliberation. We had 14 members of the committee. Each of the members actually gave his or her opinions. We were talking, discussing, and when things are very close, it's always very difficult to decide. And yeah, but in the end, you have to decide if you don't want to miss dinner, right? So we did. So I want to just tell you like what I feel, and it's my personal summary, what in the end made us pick 1 out of the 5, although we felt that all were really great. And there were a few things. So the first is, I think, what is the spirit of the Dream Chemistry Award competition, and correct me if I'm wrong, and I think what we're aiming at, we want to see the fine balance between the dreamy part and, let's say, the reality part. And dreamy means, I mean, we're looking for projects that are more dreamy than an ERC proposal, okay? And the reality part is we're looking for projects where we could have a good hope that our children will see it actually come true, right? So that's kind of the balance we're looking for. And that's very important for us when we're deciding. Like, we're trying to pick up the project that was the best, because they were all good, but that was the best in this, finding the balance. And another thing that came very important this year was like discussing the unity between the content and the form. because all the talks were excellent, both in content and in form, but some were like stunning in the form. And we really had to kind of think, where do we put the emphasis more? Or you know what I mean? I mean, both is important, but in the end, we said it's always the content before the form, so that's where we put more emphasis. That's what I want to say. And I think that's all. In the end, we came to a decision, and okay, one last thing I want to say is, although in the beginning, when we made the round and we said like our preferences, they were not the same. They were actually, all the names showed up. In the end, when we came to a conclusion, I made a round around the jury members, and I asked every single member, are you happy with the decision? And we all were, at least verbally. There was verbal consent, and sober at that time. So I think it's valid. So without further ado, let me announce the winner of the 2021 Dream Chemistry Award competition. And the winner is Jarad Mason. Jarad, please. Get the box too. Okay. It's written here, Robert Hollis. No. Okay. So Jarad, here is your award. I don't want to talk. And it's yours. It doesn't mean like next year we'll take it away from you. Just for the record, it's not Stanley Cup. Thank you. Oh, okay. So, yeah, technical comment. We are aware of the fact that it's heavier than visual prices. So, if you think you can carry it, it's okay. If you don't think, we'll fix it. Okay, yes. But this was off the record. Yeah. Mm-hmm. Okay, so, put it there, and now we come.
Magnifique.
It was a good idea, Bara. Now, Jarad, you have to pay a price. And the price is, you will tell us not what you're dreaming about, but what we're actually doing, and we're very much looking forward to it. It's all yours. The floor is yours. And Robert,
Good job.
thank you.
Good job, man.
À la prochaine. Jarad, and technically it's the same like yesterday. You have 45 minutes to talk, 5 minutes for discussion. I'll let you know after 40 minutes.
Okay, thank you very much. It's a tremendous honor to win the Dream Chemistry Award, and I have to say I'm actually quite surprised. I don't know how I would have chosen. All the finalist talks were really, really impressive, and so it's really an honor to have been selected, and happy to have an opportunity to tell you a little bit more about some different research projects in my group today. And so I thought today, if I was given an opportunity to give a talk, I would give you a summary of some very different kinds of research we're doing from the Dream Chemistry proposal that I presented yesterday. At a high level, the research in my group involves a few different areas, most of which are unified under the general theme of trying to control either porosity or some type of phase transition in a material, and often a metal organic material for a variety of different purposes. And so in my dream proposal, I talked about some of our work toward controlling porosity inside liquids. And so I thought today I would give an example of some of our work that's related to controlling phase transitions in materials, in this particular case for some more energy-related applications. And so I'll just dive right into the particular project that I'd like to discuss today, which is really motivated by the tremendous amount of energy that's consumed globally for cooling. So right now, roughly 20% of global electricity, so of the 4,400 terawatt hours that are produced for electricity annually, is used for cooling, used to power air conditioners, refrigerators, and heat pumps all across the world. There's currently about 4 billion cooling appliances that are in use globally, with 10 new cooling appliances added roughly every second. In addition to the tremendous amount of carbon dioxide that's emitted in producing the electricity required to power this cooling, there's also a large environmental impact associated with the fluorocarbon-based refrigerants that drive the vapor compression systems that power most of the cooling around the world today. And so these fluorocarbon refrigerants, like you see here, have a large number of highly polar carbon-fluorine bonds. These carbon-fluorine bonds are very good at absorbing infrared radiation right in the atmospheric IR window of between 800 and 1400 wave numbers. And so they can have incredibly high global warming potential, so almost 1,000-fold greater than carbon dioxide. Carbon-fluorine bonds are also very stable, and they tend to persist in the atmosphere for really long periods of time. So we replaced chlorofluorocarbon refrigerants with fluorocarbon refrigerants as part of the Kyoto Protocol. Chlorofluorocarbons were destroying the ozone layer, but fluorocarbon refrigerants are contributing significantly to global warming. And during the routine installation, operation, maintenance, and decommissioning of most vapor compression refrigeration systems, there's a tremendous amount of these fluorocarbon refrigerants that leak out into the atmosphere and make not insubstantial contributions to global warming. So this collectively represents over 10% of global CO2 emissions. And so there's the need for cooling is going to continue to increase as global population continues to increase. And in particular, as the developing world, as more and more people have a desire for cooling, and as the climate continues to warm, this is really not going to change. Doing something to replace fluorocarbon-based refrigeration systems is really challenging. There's really not great alternatives for the existing fluorocarbon refrigerants that we're currently using. It's really hard to find materials that have both high performance and don't have additional safety hazards or environmental implications associated with them. And so this is a really big challenge to find low global warming potential, high performance, safe refrigerants that could be used. And so there's a lot of interest in thinking about alternative approaches to cooling beyond just expanding and compressing a fluorocarbon-based refrigerant. This cooling technology was really developed in the early 1800s. Actually, the first patent was filed just north of Boston, where I'm currently living. And the refrigerants have evolved a little bit over time. The basic idea of compressing a vapor, undergoing a condensation to a liquid, expanding it back into the vapor phase to drive a cooling cycle really has remained fundamentally unchanged. And so there's been a lot of interest over the last few decades in trying to think about alternative approaches to driving cooling cycles. And one of the most simple you can imagine is, rather than undergoing this kind of vapor-liquid type phase transition, trying to drive a cooling cycle entirely in the solid state, where you don't have to worry about any direct emissions from volatile refrigerants. And so you can imagine if you had a solid material in which you could apply pressure to that material and induce an increase in temperature, If you could do that, this kind of effect is what's known as a barocaloric effect. So baro meaning related to pressure, caloric related to heat, so a pressure-induced temperature change inside a material. If you could do that, you can dissipate the heat that's generated to the environment, to a heat sink, reverse the application of pressure, so remove pressure, and induce cooling, temperature decrease in your material, put it in contact with the heat source, which you'd like to cool, and imagine operating this cyclically to drive a cooling cycle. If you think about doing this, you need the ability to have a solid material that can go between two states that have the same temperature, but in which you've been able to dissipate excess heat to the environment and then take in more heat. And so the only way you can think about doing this is if you have two states of a material that can exist isothermally at the same temperature with very large differences in entropy. And the differences in entropy between these two states of the material is going to be directly related to how much heat you can withdraw on a particular cooling cycle. And so if you want to think about materials that have large entropy changes under very similar sets of conditions, you typically are going to be interested in a material that undergoes some type of phase transition. And a first order phase transition where application of a small temperature change or application of a small stimulus, like a small increase in pressure, can induce a really large entropy change in a material. And so what you would really like is a material that undergoes some type of first order phase transition between a low entropy, more ordered, and high entropy, more disordered state. Because if you have a material that undergoes this type of transition, these types of order-disorder transitions are often associated with large volume changes. Typically, as you go from an ordered low entropy state to a more disordered state, and this involves an expansion or increase in volume. And so if you imagine starting to apply pressure to a material, so hydrostatic uniform pressure around the material, as you start applying pressure, you're going to be favoring the more compacted ordered phase. So you're going to be shifting the phase transition temperature, or the phase transition temperature to higher and higher values as you start applying pressure. And so if you have a material that undergoes a large entropy change, meaning you can withdraw a large amount of heat in a given cooling cycle, and high sensitivity to pressure, then you can imagine employing the type of cooling cycle I showed on the last slide, where you have an increase in pressure that drives an exothermic phase transition that allows you to dissipate, that can then be dissipated, that excess heat to the environment. That transition can be reversed to induce cooling, and then you can drive this cyclically between these two different states to drive a cooling cycle. So you want a material that undergoes a transition with a large entropy change that's very sensitive to pressure. You also have to consider the reversibility of these phase transitions. So typical phase transitions, first order phase transitions in materials do not look just like I drew them here, where they're infinitely sharp and completely reversible, but they often have a degree of thermal hysteresis that's associated with them. And the magnitude of thermal hysteresis, so the difference in temperature between the forward and reverse transitions at a given pressure, has a direct impact on the efficiency of a given cooling cycle. And it also impacts the pressure that's required to actually be able to drive a phase transition in a material reversibly. So if you have large hysteresis in your material, you have to go to much higher and higher pressures in order to be able to induce the phase transition in a reversible rather than irreversible fashion. And we'll return back to this point a little bit later. But for a refrigeration system, you ideally want to be able to drive a cooling cycle reversibly by applying as little pressure as possible. And so having low hysteresis is very important. So over the last 10 years, there's been a lot of interest in looking at different classes of both inorganic and organic materials and evaluating their potential for barocaloric effects for solid state cooling. However, it's been very challenging to find materials that undergo phase transitions that feature both high entropy changes and low thermal hysteresis and high sensitivity to pressure at or below ambient temperature. There's just really not that many materials that exist in this regime. And so my research group got interested in this challenge a couple years ago. And in particular, we were inspired by the fact that very simple phase transitions of just normal hydrocarbon molecules, so things like wax, going from a crystalline solid state to a disordered liquid state, feature very high entropy changes these entropy changes for this kind of melting transition is actually higher than the liquid to vapor phase transition of a typical fluorocarbon refrigerant. And this comes from the increase in conformational and vibrational and translational degrees of freedom that hydrocarbon molecules have as they transition between these two states. And so we became really interested in thinking about, could we have similar types of hydrocarbon chain disordering transitions in the solid state that might be useful for this kind of solid state cooling cycle? And so we were in search of different classes of materials where one has ordered arrangements of confined hydrocarbon molecules that can undergo thermally induced transitions to these disordered states. And we wanted to evaluate their potential for barocaloric cooling. And so the particular class of materials that we became most excited about are what's known as two-dimensional metal halide perovskites. And so I'll just walk you through a little bit about what these materials look like. So these contain octahedral transition metal centers that are coordinated typically to 6 anionic halide anions. These form infinite two-dimensional sheets, such as the one shown here, where you have corner-sharing halides that connect all these different metal cations together. These two-dimensional sheets, you have a divalent metal anion, and you have 6 monoanionic halide ions. So these are negatively charged. So you have these negatively charged pockets between all of these different axial halides. And these negatively charged pockets can accommodate different organic cations. So, for example, the alkyl ammonium cation that I'm showing here can sit right in the center of these pockets. And so if you use long chain hydrocarbon molecules, you can actually form really nice ordered organic bilayers at the interface between these two-dimensional inorganic sheets. And this has been known really since the early 1970s. There was a lot of interest in studying these types of materials as models of lipid bilayers and also as ways of understanding magnetic properties of two-dimensional inorganic materials. But what got us excited about this class of materials was that if you heat them up, these ordered organic hydrocarbon bilayers undergo transitions to a disordered state. And for hydrocarbon chains in the realm of about 10 carbons long, these transitions occur very close to ambient temperature. These transitions are associated with large entropy changes that result from the fact that this is basically like a solid state melting transition. So the material stays a solid, the inorganic layers aren't changing at all, but the increased disorder of these organic molecules leads to a large increase of entropy. And this results from rapidly propagating carbon-carbon gauche bonds throughout these hydrocarbon chains. So in the ordered phase, you have all trans carbon-carbon bonds within your hydrocarbon molecule. In the disordered phase, things start spinning around, and you have these carbon-carbon gauche bonds that propagate through the hydrocarbon chain. These transitions are also extremely reversible, and they occur with very little thermal hysteresis because of the confined nature of these hydrocarbon molecules, so they can't really move around very much. So a really talented graduate student in my group, Jin Young, got excited about this and started exploring different two-dimensional perovskites, some existing and some that he synthesized, and looking at their phase change properties to try to identify an initial target that we could explore to evaluate how useful these materials would be for solid-state cooling. And he identified a particular 2D perovskite that is composed of a manganese cation, chloride anions, and a decyl ammonium C10 hydrocarbon chain, structure of which is shown here. And this 2D perovskite undergoes an order-disorder phase transition slightly above but very close to ambient temperature that's associated with quite a large change in volume, so about an 8% overall expansion in volume as the distance between these inorganic sheets increases as you go through this phase transition. And so we were excited about this because of both the large entropy change associated with the phase transition and the very small hysteresis as well. And so we wanted to start exploring its sensitivity to pressure. So using just a simple thermodynamic relationship, the Clausius-Clapeyron equation, one can predict how much this transition temperature will shift as you start applying pressure. And this value was much higher than other materials that had been reported for barocaloric cooling. And so we were quite excited about that. So in order to evaluate the phase change thermodynamics, so how the entropy and enthalpy and transition temperature change as a function of applying pressure, we perform experiments that are known as differential scanning calorimetry experiments. So these are experiments where we're at a constant pressure and we're changing the temperature of our material and monitoring the flow of heat in the system. So simple kind of calorimetry experiments where you are measuring the thermodynamics associated with the phase transition. So at ambient pressure, as we heat our material and we start to induce the transition, we see a negative heat flow signal that's associated with an endothermic transition. So this is like the solid state melting transition going to the more disordered phase. And then upon cooling, we see an exothermic transition associated with the reverse transition back to the more ordered phase. And so we can start evaluating these phase transitions as we start increasing pressure and going to higher and higher pressures. And we see that the phase transitions shifts in temperature much as we expected based on our prediction using the Clausius-Clapeyron equation. But what we really want to be able to do is not to evaluate how much the phase transition temperature shifts as a function of pressure, but to evaluate how much entropy change we can induce by applying and removing pressure to the material. And so that's what we were set out to do next. And so I'll just very quickly walk you through some of the thermodynamics behind how we think about doing that. But I'm going to go through this relatively quickly just to get to the conclusion. So the experiments we do are isobaric, meaning they're done at constant pressure. But what we'd like to do is get information about what will happen under a constant temperature environment. So we can convert this raw heat flow data to entropy data as a function, entropy as a function of temperature. And we can calculate the change in entropy for different pressures. So here all we're saying is that we start at the low entropy ordered state of our material. As we increase temperature, we undergo the phase transition to the disordered state. And the temperature at which this happened increases as we increase pressure. And this is where the thermal hysteresis associated with the phase transition becomes really important. So when we're thinking about evaluating the entropy change associated with compressing or applying pressure, we're most interested, the data that's most relevant corresponds to the DSC data from cooling curves. Because cooling is what's inducing this transition to the more ordered state, just like compression. Alternatively, when we're thinking about removing pressure from our material, that's inducing the transition to the more expanded, disordered phase of our material. So it's going to be analogous to the transition that's induced by heating. So there we care more about the data from heating. So we can use this to generate what are known as isothermal entropy curves. So these are the constant temperature changes in entropy as a function of temperature. And the main thing to notice here is that the forward transition, the transition that's induced by compressing from 1 bar to a higher pressure at 40 bar does not have any overlap with the reverse transition that's induced by going from 40 bar to 1 bar. And that's because of the hysteresis associated with the phase transition. So what this means is that between 1 bar and 40 bar, you cannot drive this transition reversibly. If you start in the disordered state and you apply pressure to induce the transition back to the ordered state, you can do that once, but when you remove pressure, you'll stay exactly where you are. So you can get one temperature change, but you can't cycle between 2 temperature changes, so this is completely useless for driving a cooling cycle. If you go to higher pressures, though, then you start to see some overlap between these isothermal entropy curves, and now you can at least partially drive the transition in a reversible fashion. So now you have some hope of being able to actually drive a cooling cycle. And as you get to higher and higher pressures, the region of overlap increases. So this really highlights the importance of really driving down hysteresis so that you can operate a cooling cycle at as low a pressure as possible. And so in evaluating the properties of these materials, there's 2 features of these DSC curves that are really important. One is the width of these transition peaks, and the other, as I mentioned, is the hysteresis associated with these transitions. And so one thing my lab has spent a fair bit of time on is trying to understand what are the specific factors that contribute both to hysteresis and transition width? What is actually intrinsic to the composition of a particular material, and what is extrinsic? Meaning, what depends on kind of how you pack your sample together, particle size, degree of thermal contact in the experiment, and other factors like that. And so, just skip this. But what we found is that for these 2D perovskite materials, as two-dimensional materials, they tend to form really large flakes that kind of stack together, but do not pack together particularly well, and do not have really great thermal contact with their surrounding environment. And this leads to thermal gradients as you're increasing and decreasing temperature that broaden the phase transition. If we grow single crystals of these materials, and some of the single crystals that another student in my group, Rahil, have grown are shown here, about 50 to 100 microns in size. If we do these experiments on a single crystal rather than a packed powder, where we have really nice thermal contact between our heat source and heat sink, we see significantly sharper phase transitions. And this is really important for thinking about the amount of pressure that's required to induce a phase transition reversibly, and really emphasizes the importance of thinking about thermal contact when you're thinking about these types of phase transitions in the context of solid-state cooling. And this is a point that had kind of been overlooked actually in most of the literature in this area. And so when we look at our single crystal samples that have really good thermal contact, we're now able to induce reversible isothermal entropy changes about 3 times higher in magnitude at an equivalent pressure. But still, the temperature range over which we can induce these reversible entropy changes is quite modest compared to what you would actually need to be able to have a useful cooling device. And so this is one of the other reasons we were really excited about this particular class of materials, of 2D perovskites, is because of their tremendous tunability. Right? So we can think about making all kinds of modifications to the different components of these lattices to tune and optimize their phase change thermodynamics. So we can think about tuning the interactions between the organic layers within these 2D perovskites. We can think about tuning the interaction between the cationic head group of these alkyl-ammonium chains and the anionic pockets of the inorganic sheets, as well as the interactions at this organic-organic interface. You can think about functionalizing these organic molecules, swapping out different halides, different metal cations, and all kinds of things like that. And so an undergraduate researcher in my group, Selena, has explored a really wide range of different kinds of functional groups that can be present in the organic bilayers of these materials, and started establishing relationships between phase change thermodynamics in these different kinds of structures. And so I'll just highlight one example of a particularly interesting compound that she found, which has the exact same structure as the manganese 2D perovskite I was talking about previously, but now we have copper and bromide atoms in the inorganic lattice and a C9 rather than C10 chain. But this material undergoes a similar type of order disorder phase transition with a relatively high entropy change, but really low thermal hysteresis. So reversibility on the order of less than half a Kelvin. And the reason we think that this material undergoes a phase transition with much lower hysteresis than the previous material I discussed is we think has to do with the fact that we're adding in these larger bromide anions compared to these smaller chloride anions. This increases the cavity size of where the ammonium group of our alkyl chain is sitting. And it leads to slightly more disorder that's present in the lower temperature phase of this material. So we still undergo a transition from a more ordered to a more disordered state. But the transition has a smaller entropy change, and this lower entropy state is actually closer in structure and dynamics to the higher temperature state. And so we think that there's a better match between these two phases, and so there's a lower activation energy barrier to nucleating one phase from the other, and that's what leads to this smaller hysteresis. And so we can kind of see this in the heat capacity of this material, where we see a broad feature that's consistent with gradual activation of molecular motion in the low temperature phase of this material. And we also see this in infrared spectroscopy as well. And as I mentioned, we think this is due to the roughly 15 to 20% larger cavity size of this bromide anion. So this material has a similar kind of sensitivity to pressure as the first compound I described, actually a little bit higher sensitivity to pressure. And what we were most excited about this material is that because of the really low hysteresis, we can actually drive phase transitions reversibly at really low pressures. So pressure now of just 16 bar. For reference, most of the barochloric materials that have been reported in the literature previously required pressures on the order of thousands of bar to operate reversibly. So this is something we're really, really excited about. And so we can do similar kinds of thermodynamic analyses to evaluate the magnitude of the reversible entropy change that you can induce, i.e. how much heat you can withdraw on a given cooling cycle by operating the phase transition reversibly. And we see similar kinds of effects as we move from a powder sample to a single crystal sample with high quality thermal contact. We get really sharp and sort of sharp phase transition peaks. And so now we can drive phase transitions reversibly by swinging between just a pressure of 1 bar and 150 bar, so a relatively small change. We can drive large entropy changes over a window of about 2.5 Kelvin. And so this is a wide enough temperature window that you can actually start thinking about making a practical cooling device. Because with this much of a temperature window, you can start employing things like regenerator schemes and more complicated kind of engineering schemes that will allow you to have really large temperature differences between your heat source and your cold source, much larger than just this 2.4 Kelvin. And so this is something we're super excited about. And so I'll just summarize this portion by saying that we think 2D perovskites and other kinds of layered materials that feature these kind of ordered hydrocarbon layers provide a really rich phase space to explore in the context of solid-state cooling applications. And here I'm just comparing some of the materials we've made, including a few that I didn't have time to discuss, to some existing materials and highlighting the high sensitivity to pressure and low hysteresis that's present in a lot of these materials that allows us to drive reversible cooling cycles at extremely low pressures. And so we're really excited about continuing to explore this. So I thought in the remainder of time I would tell you about something actually even more different from this, but that still involves thinking about manipulating phase transitions in a metal organic material. And so I'll kind of just abruptly switch gears to tell you about a different project in my group that involves trying to think about ways of making new types of glassy materials. And so our interest here is in particular trying to think about applying coordination chemistry type principles to be able to control local structure and also porosity or free volume within a glassy material. And I'll tell you a little bit about why we're interested in that and how we're approaching trying to do that. So glasses are actually tremendously important materials and support a lot of our modern technology. In comparison to crystalline materials, they have a number of unique characteristics, including optical transparency, like our windows in this room, a lack of grain boundaries. They can be very processable. And they find use, as I mentioned, across a wide range of different applications. And the need for new types of glassy materials is only going to continue to increase. But for right now, the structural and chemical diversity of glasses really pales in comparison to the structural and chemical diversity of crystalline materials. And so the most common types of glasses are those based on silica, a few different kinds of chalcogenide-based glasses, polymers, and metallic glasses. And glasses that offer access to new structures and properties have the potential to make a tremendous impact across a wide variety of different areas. In particular, glasses that have controllable porosity offer opportunities for gas separation membranes, such as those that might find utility in capturing carbon dioxide from power plants. Also, glasses or materials that can switch between a crystalline and glassy state have opportunities for new types of memory materials, And glasses are very much of interest for solid-state electrolytes and batteries, in particular because of their lack of grain boundaries and increase in free volume in comparison to crystalline materials. So one class of materials that's notably absent from the list of common types of glasses are metal organic materials. So materials that contain both organic and inorganic units. And so yesterday I talked a little bit about one of these classes of metal organic materials known as metal organic frameworks, where one has an inorganic unit or a metal cation that's connected in 3 dimensions by a bridging organic ligand to form a crystalline, porous, 3-dimensional framework. And so metal organic frameworks offer a number of advantages in terms of being able to control local structure within a material. By tailoring both the bridging organic ligand and the inorganic unit, one can very predictably modify local structure within an extended material and tune the properties of the material as well. And this also provides opportunities for controlling the free volume or porosity within a material. And so if you could think about applying similar types of coordination chemistry principles, not to the ordered crystalline phase, but to the disordered amorphous or glassy phase, then you would have a lot of opportunities for being able to control the local structure of a glass in a much more predictable fashion and tunable fashion than is possible in other types of materials. And also to think about controlling local distribution of void sizes and shapes within a glassy material. But getting a metal organic framework type material to undergo a transition from the crystalline solid state to a liquid that can be quenched into a glass is really not an easy task. There's only a few examples of different types of metal organic frameworks that undergo transitions to form a glass, and most materials will thermally decompose before they undergo a melting transition. And so the synthesis of glasses is a non-equilibrium process. Glasses are metastable with respect to a crystalline state. And the nature and the structure and properties of a glass depend a lot on the process by which it was formed. So exactly how and quickly and from what temperature it was quenched in the molten liquid state. And so melt quenching is really one of the most powerful ways of producing a glass. And being able to melt quench and form a glass and to evaluate how different non-equilibrium conditions influence the structure and properties of the resulting glass, of course, requires being able to access a stable liquid phase of a material. And as I mentioned, this is something that's really challenging to do for metal organic frameworks. And so this table shows all of the examples of 3-dimensional metal organic frameworks that can undergo a transition from a crystalline solid phase to a molten liquid phase. And what you'll notice is that there's very little structural and chemical diversity within these lists. So these are all almost exclusively zinc azolate based framework materials that undergo melting transitions at very high temperatures that are actually irreversible. So a lot of these materials start to decompose immediately once they're in the liquid state. Just for reference, there's something on the order of about 80,000 different metal organic frameworks that have been synthesized and structurally characterized. And so this is an incredibly small subset of materials compared to all that is out there. And so my group became really interested in thinking about rational thermodynamic strategies for bringing down the melting temperatures of metal organic frameworks to provide access to a much wider range of materials that can be converted into a liquid that could be then quenched into a glass. And so in particular, we were interested in trying to develop ways of bringing the melting temperature of these extended materials below the thermal decomposition temperature. And so we developed a number of thermodynamic strategies for thinking about how to do this, including trying to really weaken the interactions between bridging organic ligands and the metal cations of our materials, trying to incorporate additional conformational flexibility into our bridging organic ligands to have very low symmetry organic ligands that would provide an increased entropic driving force for conversion from the crystalline solid to the disordered liquid. And so I'll just give you an example of one class of materials we've developed that really allows us to do this. So this is a class of metal organic frameworks that's composed of a divalent metal cation that's bridged by this bis-acetamide kind of bridging ligand. These form three-dimensional extended frameworks that are cubic in their overall structure. And these undergo melting transitions to form very stable liquids at much lower temperatures than had been possible for any other kinds of extended materials. And we spent a fair bit of time trying to unravel different kinds of thermodynamic relationships and understanding how different structural and chemical changes to these materials influence the enthalpy and entropy changes associated with these melting transitions. But I won't really get into those details. I'll just kind of highlight that these materials offer access to a wide range of different glassy phases through melt quenching reactions. So if we take these materials, induce the melting transition, quench them to form at relatively quick temperatures, we can undergo transitions to form a glass. And certain kinds of materials, other materials will recrystallize very quickly, and it can be very difficult to access a glass phase. So we've spent a fair bit of time trying to understand how we can tailor these materials to tune the kinetics of these crystallization versus glass transitions. We can also look at exactly how the structures of these extended frameworks changes as we go from the crystalline solid state to the liquid state and then back to the glass state. So we can do XAFS experiments, extended X-ray absorption fine structure experiments, where we shoot an X-ray beam basically at these materials. And this will eject an electron specifically from the metal atoms within the material. And then we effectively look at interference of this electron as it leaves the metal center. And this tells us about the local coordination environment around the metal. And so what we find is that in a lot of these materials, the local coordination environment around the metal center is not all that different between the crystalline solid and the liquid state. And this is exactly what we were hoping for, because we want to be able to use these very directional bonds between our metals and bridging organic ligands to influence the average local structure within the liquid and then the glass that it's quenched from it. So we can also do pair distribution function analysis. So this is a total scattering X-ray based technique that gives insight into the local structure of disordered materials to look at the structure of the liquid states of these materials and compare it to the glassy state as well. And one of the interesting things we see here is very similar kinds of structural features at short distances, meaning that the local structure of these materials in the disordered and ordered states are very similar, even though there's no long-range order in the liquid or glass phase. And then we see correlations in the liquid, structural correlations at much larger distances, so 10 to 30 angstroms, that are indicative of preservation of longer range order that's very similar to that's in the original crystalline material. And that's kind of highlighted here. And so I'll just kind of start to wrap up by saying we can access a very wide regime of different rates of glass formation in these kinds of materials, making materials that are very excellent glass formers to poor glass formers and everything in between as well. And we can characterize these glasses using X-ray diffraction-based techniques, and we can also synthesize really large, transparent, high-quality glass films of a lot of these materials. And evaluate a lot of different glass physics type properties about these systems. What's particularly exciting about having this kind of wide tunability in terms of manipulating these glass transitions is that we can get to regimes where we can make materials that will undergo a transition from a liquid to a glass, and then upon heating can be recrystallized back into the crystalline state. And then remelted to form a liquid. And so having access to glass and crystalline states of a material irreversibly is actually something that's really challenging and also very powerful in the context of applications in phase change memory. And so in a phase change memory, one can think about storing information, so bits, in crystalline versus amorphous states of a material, as long as you have a difference in some type of optical or electronic property. So you imagine this is your 1 and this is your 0 in a storage system. And you can induce these transitions basically by taking your crystalline material, heating it up to form a liquid, rapidly quenching it to form the glass, and then annealing it back into the crystalline phase. This is typically done with chalcogenide alloys. These are the most common types of phase change memory-based materials, but these require melting temperatures of above 700 degrees C, which requires a lot of energy to use them. And so there's a lot of interest in being able to do this at much lower temperatures. And we think that our materials provide access to that regime, and we're really excited about exploring their potential for this kind of application. So hopefully that was a taste of some of the different kinds of more thermodynamic-y research that is happening in my group. I just want to acknowledge all the students that have contributed to the work that I talked about today, some of our collaborators, different funding agencies, but most importantly, just again, really want to thank the organizers for the opportunity to come here. Really honored to have been selected and quite surprised as the recipient of the Dream Chemistry Award. So really appreciate that. It's been a true pleasure to be here. Really have enjoyed the time and have really enjoyed the interactions with everyone, including particularly the other finalists, and learning about their dream proposals and their science as well. So thank you all again, and happy to take any questions.
Thank you very much, Jarad, for a beautiful talk. I mean, I could smell some dreams even in your reality talk. So, and I think it's a positive statement. So, questions, comments, Robert.
How big crystal do you need to operate a typical refrigerator?
Yeah, so one is probably not going to want to operate a refrigerator with a crystal. So, you know, I think the single crystal applications for cooling, I think, are probably most suited to electronics. And so there, having a thin film of a material on some type of piece of equipment, right, or circuit board that's generating a lot of heat makes a lot of sense. And that's something we're kind of actively exploring with those. For large-scale cooling applications, such as refrigeration or air conditioning, you're never going to be able to do that, probably, at least with the types of materials we're looking at with single crystals. And a large single crystal is going to probably crack anyway with these kinds of volume changes. So what this really emphasizes is the need to have high-quality thermal contact in your system, and to try to be able to work with high thermal conductivity materials to drive an effective cooling cycle. So yeah, that's a great point.
Yeah, thank you very much. I have a practical question to the perovskites, right? I mean, one of the, how stable are they against moisture, right? Because normally, of course, if you cool, typically you also come to condensation, and you have halides, you have transition metals.
Sure.
So
yeah.
How practical is that?
That's a good question. And, you know, I mean, for the main application of these kinds of perovskite materials is to leverage their optoelectronic properties. And so typically lead iodide perovskites, right, for solar applications. And their moisture sensitivity is a huge problem. The materials we're working with are actually really hydrophobic. They're really bad at absorbing light, mostly because, you know, we have first-order transition metals and also really long hydrocarbon chains. So they're not at all useful for solar applications, but they're quite hydrophobic because of these large hydrocarbon chains. And so we see basically no sensitivity to moisture because of their hydrophobic nature. If we start functionalizing the organic bilayers, like some of the things I showed, we're incorporating more polar functional groups, like hydrogen bond donors and acceptors that can lead to larger entropy changes and things like that, then moisture sensitivity can definitely become a problem. And these types of systems, though, they would likely be insulated from the environment because we're going to be applying and removing pressure. But that is something that one would have to consider.
Yes, so when you showed this order-disorder transition for the tells, that immediately reminded me the liquid disorder transition in phospholipid bilayers. You could also think about the octahedral phase. So how would these materials work, which are so common, so usual, and would Could you use them for cooling?
Yeah, so that's a great question. And, you know, like that, one can also think about just wax, right? And the type of transition I motivated some of this by for cooling applications. Most people are not very excited about having something that's a liquid in these kinds of applications, particularly a viscous liquid. So in trying to do something entirely in the solid state, you know, all of the benefits that are associated with a solid state cooling cycle, a lot of them are lost if you have a transition that goes to a liquid, because you have things that start moving around, and you know, heat transfer is very important. So your degrees of thermal contact will change, and you can have leakage and things like that. So
what if you have, like, say, the octahedral phase of phosphorylated bilayers? They are liquid only in the sense that the lipids move along the monolayers, but the whole material is essentially a solid, right? So
yeah, so in that particular case, I do think there is utility. And so I didn't talk about this, and I don't think I have it as a backup slide, but so we're, in addition to the 2D perovskites, we're looking at all organic materials that are very similar in nature to lipid bilayers. So these are like organic salts, effectively, but long hydrocarbon chains with ammonium head groups, and just charge balanced by like an anion, for example. And those behave very similarly to lipids, and so all those kinds of layered materials would work well. There's some other interesting aspects of this which I didn't really have time to address, but in some of these transitions, the disordered phases are really good at absorbing gas molecules. And so when you're thinking about, in all of our experiments, we're using gas to transmit pressure. And so how the gas interacts with the disordered phase of the material is actually really important. And so when you move to some of these liquid type systems that can expand a lot in the presence of a gas, that actually can create challenges or opportunities for driving these cooling cycles with pressure. And you can get some really kind of weird stuff where you're expanding your material, but because gas or your pressure transmitting medium is going into the material, you actually reverse the direction of the barocaloric effect. And so rather than applying pressure leading to an increase in transition temperature, it leads to a decrease in transition temperature. And it can be quite large in some cases. So you're expanding, but driving an inverse caloric effect. And so there's a lot of stuff we're kind of exploring in that space as well.
Right. Well, thank you very much for a beautiful talk. Congratulations again.
Thank you.
I forgot to mention, there is, on top of this heavy price, there is also a small financial premium of 10,000 euros that should allow you to cover the FedEx fees, at least, to mail it wherever you want to mail it. Yeah. And congratulations to everybody. And as a next point, I'm really happy that Magdalena Helmer, long-time editor of Nature, agreed to come here, serve actually as a member of the jury, and we really very much used her valuable input yesterday, and also to give a presentation and tell us about the insider view on what's going on in Nature. And yeah, I guess that's what we will hear, and we're really eager to see the point from inside into the journal. So Magdalena, it's ideally 30 plus 10 for you. Thank you.
Okay. So it's a great pleasure for me to be here to experience firsthand that the Dream Chemistry Award really is a quite different award than usual ones. And a big thank you to the organizing for asking me to be at this event. And thank you also for all the top finalists for sharing their inspiration and sharing their dreams. I must, okay. Okay, sorry.
Put it into your pocket, otherwise it will end up there.
So we have heard a lot about dreams here. My talk isn't so much about dreams, more about the realization and the fulfillment of the dream of a Victorian astronomer. That was Norman Lockyer, the founding editor of Nature. Nature was, the first issue appeared in 1869. I've shown that here. And we, a few years ago, had 150-year celebration of Nature. In that time, a lot has happened. Nature itself looks very different. The journal, the way scientific papers are published is very, very different. The peer review process obviously has changed a lot. At the beginning, there was no peer review at all. Even the Watson-Crick paper about the structure of DNA was in fact not reviewed. The editor at the time thought everybody could just would know immediately what it means. Referees wouldn't be able to keep quiet, so it was published without peer review. Nature also has now many little baby natures, lots of discipline natures, nature chemistry, nature physics, review papers. But despite all these different changes, the mission of Nature really has stayed the same. In 1869, and now the mission of the journal is twofold. First of all, to serve the scientific community by publishing scientific findings and providing a forum for discussion and debate. And the other, also quite important part of Nature's mission is to communicate science to the wider public. And to kind of do it in a way that becomes apparent why science is so important for knowledge, for culture, and for daily life. These two very different aspects of what Nature is trying to do mean also that the journal itself has two quite distinct sections. One is very journalistic, it's like a magazine, and the other one is more like a normal scientific journal publishing research papers. The first, Nature started off as a one-person outfit. In 1970, there were 2 members of staff, and that's the picture that was taken when we had our 150-year celebration, so 2 years ago about. And there are now more than 100 colleagues that all work on Nature, for Nature, and that includes about 30 manuscripts editors like me who handle the papers that are submitted. And we are, oops, sorry. We are organized in 2 teams, physical sciences and biological sciences. Each team has a chief editor who they report to the editor-in-chief, Magdalena Helmer. Magdalena Skipper. Well, maybe one day. Well, to be honest, I wouldn't really. I love science itself, and in my job, I think you're closest to it. So it really is actually my dream job. But she has overall responsibility for everything that's published, but in terms of manuscript handling, very little involvement. I'm showing here a slide, all the current members of just the physical sciences team. Most of us are in the London office. We have 2 colleagues in Berlin, 1 each in Washington, San Francisco, and Shanghai. And you can also see the core areas that each of us is covering. So each editor will have a field, and when a paper submitted will be assigned to an editor who handles the field where this paper mostly lies in, but we interact quite a lot, and quite often papers are seen by 2, sometimes 3 or 4 editors who provide input. All of us are fully professional, full-time editors, but we do have PhD, postdoc level scientific training. And all of us are very passionate about science, I would say. And we look forward to seeing your great papers submitted to us, so hopefully we can publish them. And so what makes the question, what makes a great paper great? People thinking about nature often think it is blockbuster science, so how to cure cancer, the latest quantum computer, so big picture science that makes the headlines. But that's of course not necessarily great paper. A great paper is that reports great science, and so any worthwhile science that's done with rigor and passion would be great science, and done in that way, looking at a big question or a small question that can make for a great paper. But of all the great papers that do arrive, quite often it is actually quite hard to reject papers. We need to look at papers for Nature. And what are we looking for? Nature is a high impact journal, so we really do need to look for impact. And that can come in different varieties. Impact on science or society could be the structure of a quite important biomolecule for the first time reported or at higher resolution. So lots of other groups will be able to look at mechanism, could explore its interactions with other biomolecules, proteins. Impact on society might be a catalyst that has been slightly improved, but makes a difference between a fuel cell being economically viable or not. We look for findings that open new areas of research that really address a key disciplinary goal. So essentially for findings that address a first order question, not for findings that provide detail that is important for people working around you, but where the ramifications, further impact doesn't really carry and travel beyond that small field. There's also another type of paper that would be like significant resource value. That might be, for example, an ice core, a paper reporting ice core data, which is very difficult to obtain, and the data could then be used by lots of different in lots of different studies, trying to reconstruct climate, trying to learn about past atmospheric composition. I myself also really like papers that report technical breakthroughs. I think often advancements in technique and method can open a new field. They really are so enabling, so that's something we are quite perceptive to. Sometimes also you have a study that is just really beautiful, very elegantly done. It's not necessarily clear what the wider implications will be or whether anybody will be able to make further use of it, but sometimes they are just so stunning that on occasion we will consider them as well. But at the end of the day, only about 20 to 30% of submitted papers are sent out for peer review. So that means a negative decision is, of course, not very positive, very pleasant. It also takes time. So thinking whether to publish in Nature or in any journal actually that is having some selectivity with respect to what it does publish, it's a good idea to try and pitch the paper at the right angle, and there is not really a secret formula. At the end of the day is the research question that's addressed and the quality of the data that are the key. And trying to step back from your own research, which is very exciting and interesting for you, and trying to see it in the bigger picture and seeing how important the findings really are when you step back, and gauging that against what is published in different journals helps to hopefully target the paper at the right level. Oh, shit, sorry. And then when it comes to putting together the paper, helpful to think of not only that you want to get your work out, but the readers and users. And at Nature in particular, lots of people think it has to be blockbuster science, so the science is really sold quite heavily. It's something that puts off most of my colleagues, well, all of my colleagues, and it also, I quite often see that it puts off referees. So really, it's so beautiful if people just let the science speak for itself. So just explain and don't hype, and show and don't tell. With that I mean just really also show the data that underpins what you are concluding, what you're stating. When putting a paper together, especially for a journal like Nature or one of the Nature research journal, it's very helpful to have the context briefly outlined, just to explain what the problem is that is being addressed and why you have picked that problem. The focus, really writing the paper so it's not too diffuse, not all the observations and along the way are described in too much detail, but really what is the one most important thing to take home. And doing so clearly, succinctly is helpful. Makes it for us as editors and readers helps really kind of having a positive attitude to the paper, and also keeping in mind that it's any paper will be one stone in one wall in the wall of bigger science that is being built. So it's just a stepping stone. It's not the very final end. It really ideally should help others to go further. And keeping a paper brief, to the point, and clear is very helpful. Everybody is busy, authors, referees, editors, so getting the key point across makes it more pleasant to deal with the paper. If you've decided to submit to Nature or to any journal, the cover letter is a great opportunity to help putting across why you're excited about the work, why you would like the journal to consider it. I always read first the whole manuscript. I try to get a good feeling for what people are trying to achieve, what the key findings are, and after that I always read the cover letter. And if authors use it well, it's like 10 minutes in the room, and you can really tell an editor why they should consider it. And doing that briefly in a to-the-point fashion is helpful. Sometimes I have cover letters that are almost as long as the paper. And if an author struggles to really make the point, why is it important, it's often suggests, well, maybe it's not for Nature then. It's also good to make referee suggestions. It's always helpful to have them if they are really useful. Sometimes referees are suggested that don't even work in the field, collaborators. But if they're good suggestions, it's very much appreciated by me and all my colleagues. Referee exclusions, we tend to always honor that, but not more than about 3 to 4 people. It's also helpful to know why. I once had an author who wanted me to not use any scientists from a pretty large continent. So it has to be realistic, and quite important that we are told about related papers that are elsewhere. And after the paper is submitted, papers are assigned to editors according to the field. We make our first editorial decision, often almost always in consultation with some of our colleagues. Only about 20 to 30% go for peer review. Peer review at Nature was only really started in the 50s. And we try to make this initial assessment in about 2 weeks or so, 1 to 2 weeks. We aim for 2 to 4 reviewers per paper. Occasionally there will be more. And try to get a first decision to you within about 1 to 2 months or so. when we try to find referees, I only have data from 2011, but then all the nature journals used roughly, not quite 20,000 referees, and only 2.5 of them refereed 3 or more papers, so it's quite a large range. We always try to increase our referee pool. We typically, select about 2 to 4 referees, obviously on the basis of the technical expertise. That can sometimes mean we have to go to quite a few more referees in case there are important methods used that all need to be evaluated. And we try to also have a referee who has a good overview to comment on the advance of the findings being reported. And referees are known to be fair and constructive. In particular, there's such a big difference between reports. Some spend a lot of time evaluating the work and thinking how they can provide feedback, even if it's negative, that it is helpful to the authors. And those are referees that are very valued, and we share. So we ask referees to comment from 2 different perspectives, essentially. One is the technical evaluation, which is, of course, really important. Do the conclusions hold up? And is the quality of the data acceptable? Are all the necessary controls there? And is the work meeting standards in the field? And we also ask for subjective evaluation, the feeling of, or the impression of just how important are the findings and how likely are they to really advance the field, maybe have also a wider impact. And once we have our reports in, one editor will look at them first, usually discuss with 1 or 2 other editors, and we make our decision. And the decision is not just the counting of votes. We try to look at the scientific arguments, of course, and it's relatively common that referees will disagree in their overall evaluation, and that's obviously quite understandable because they usually come from slightly different perspectives. The referees we choose won't all work in exactly the same field, so they come have a somewhat different background. And we as editors can overrule referees. The referees are primarily there to give technical evaluation of the paper. And subjective points, it's easy to overrule them. We rarely overrule we don't overrule on technical negative comments that refer to that question the main conclusion of the paper or a really important aspect of it. Sometimes there are technical points that are really affecting a minor part of the overall study. Then we might feel, okay, the work has gone sufficiently far. It would be nice to cross a few more T's and dot a few I's, but that might not be necessary. So ultimately, it is not the referees that decide what to do. So, and then our decision can come in different flavors. Obviously, a straight reject, and it looks unlikely that the study is salvageable. Quite often that is because of concerns about the limited advance over what went before. So the paper just isn't sufficiently significant for nature. The majority of decisions will be a revision of some sort. Sometimes it's, well, if you really could show what you claim there, which is quite spectacular, we would definitely be interested, but it just seems so unlikely that the technical problems can be overcome, or more encouraging inviting a revision. So a few more controls need to be done. And of course also accept in principle. I don't think I've ever had a paper that could be fully accepted, because we have to ask authors also for formatting, changes to the manuscript. And when we ask for a revision, which is already a pretty positive outcome after peer review, we expect that authors address all the issues and ideally experimentally as well. We always ask for point-by-point response to our reviewers, and sometimes referees will make points, will ask for controls that are simply not feasible, and it's obviously fine. Just tell us why something isn't possible. Most papers will go through 2 or 3 rounds of review, so referees will see the revised paper and the responses. So it's quite a big difference in how then further revisions go. Depends on how authors take the criticism of the referee. Some get really upset and see what's raised as a an insult on them, questioning of their work, and respond in an emotional manner. It's unhelpful. Even if at first seems unreasonable what the referee says, almost all comments, you can get something out of it. So it is an opportunity to really learn. Maybe it also was simply that the paper wasn't very clear. Even what the referee has said doesn't make any sense. Maybe look at the paper. So yes, responses always should stay professional, and persuasion and diplomacy are the key to move the paper forwards. And if a referee makes comments that indicate that the paper hasn't been understood, then that obviously is a quite big problem, irrespective of the paper will be published or not. If we end up declining the paper, we are always open to appeals, both after an editor has made the decision and also after it has gone through peer review. And new data is often a reason for authors to get in touch with us. And in such cases, appeals tend to be quite successful. When referees or editors make errors or have simply overlooked something, obviously get in touch, let us know. And if response to the referee is carefully phrased, referees, in my experience, also are quite amenable to being shown that they are wrong. I mean, some people have don't like that, but in the majority of cases, people are quite amenable. Referee bias is always a possibility. I think it's quite rare that it really decides the decision, causes very clearly controls an overall decision. But if authors suspect there is bias, we are open to being told and shown that that really is the case. But that's, in my experience, quite rare. We regularly receive appeals that are simply a slightly hashing of the paper, or it has been newly submitted without the previous version having been mentioned, in the hope that maybe a new editor looks at it. But that rarely, that doesn't change our decision. We have had cases where authors wheeled in a Nobel Prize winner saying how great the work is. The Nobel Prize winner worked in a different field, but it's a big name. And that's also not very helpful. It does happen, unfortunately, that there are personal attacks, very disparaging comments on referees, sometimes editors. I think there had been a case where it was requested that the female editor should be replaced by a male editor. I think, I do understand that authors are passionate about their work, they prepare it carefully, not all of them, and it's their baby and they sent it and get back, no, thank you. So I understand that people are quite emotional and it's not nice. It can have quite some implications career-wise for especially the young students. But keeping it personal is and diplomatic is definitely the more effective way to handle that. We often also have authors that then draw attention to other published papers. You know, my paper is really quite similar, you published that, so why am I getting rejected? But, you know, that's not very helpful. It's very rare that studies are directly comparable and science also progresses. So, you know, a paper last year or 2 years ago will have arrived in a different scientific environment, different time. So comparison to other papers is also not very helpful. If we are not able to publish a paper in Nature, we have another quite a large number of other journals that authors might wish to consider. Nature is the most selective journal in the group, and there's a lot of processing of the paper. The figures are worked a lot on. There's a lot of copy editing. At the bottom or base of this Christmas tree is Scientific Reports, which is not a Nature journal, but it's also the same publisher, which is not really very selective. As long as the science is correct, the journal is happy to publish the paper. And in between we have communication journals. They are the latest edition, Nature Communications, that is also interdisciplinary like Nature itself, just the impact is quite a bit lower, and the Nature research journals. Nature now, since quite some year, offers the opportunity for authors to transfer their papers after they have been rejected from journal to another. We send our decisions by email, and there's always a link that authors can use. When authors submit a paper to us, they also have, at submission stage, the opportunity to indicate whether they would like us or would not like us as editors to consult with other journals, and that is a function that really is meant to save time. Authors and also journals and referees. If authors give us the permission to do these consultations, we will, talk to our equivalents in Nature Chemistry, Nature Physics, Nature Materials. Sometimes, when we receive a paper before deciding for peer review, or we decide we can't peer review it, but think it's a really nice paper, it might find a really good home in Nature Chemistry. I sometimes consult with colleagues there and tell them, and then it's very nice being able to tell authors, sorry, we can't publish a paper in Nature, but I know Nature Chemistry, this colleague, he told me he would be very keen and would send it out for peer review. And the same after peer review. Yes, this ability to consult is very valuable. And I'm not quite sure whether authors always understand what is involved in that. When after peer review, if a transfer is done, both referee reports and the name of the referees will be transferred, and then the editor at the receiving journal saves quite a lot of time, has a lot of information, and if it was possible to consult before, sometimes based on the review process on Nature, they will offer to publish it. That has occasionally happened. If authors prefer that that doesn't happen, they can just let us know and we won't consult. And with that, I thank you for your time, and I'd be very happy to take any questions.
Thank you very much, Magdalena, for this deep insight into the nature from within. And yeah, I'm sure there will be questions and comments from prospective authors, right? So, Claudia.
Thank you for the talk. I have a couple of questions for young researchers.
Yes.
One is about reviewers. How often do you ask young researchers to be reviewers in Nature papers? And how do you go about, I mean, how do you trust them in the same way you would trust more experienced senior researchers? And the second question is about, I've attended a talk given by an Elsevier editor, and they said that they also look at the citations and H index of the last and corresponding author of some papers. Of course, this for young researchers is a bit problematic because at the beginning, of course, numbers are lower. So I'm just wondering whether this is something that you also do.
I didn't quite understand. They look at it for what purpose? For selecting a referee?
First, no, that's for publishing. They look at it in terms of to decide whether the paper is interesting enough or can be sent out for review or should be rejected, and they are influenced by the H index and the number of citations and everything, because when you were mentioning before that you look for impact, sometimes, of course, to keep a high impact factor, you also need to have the paper cited and so on. So
yes, it's a.
So I'm just curious about these two aspects, having how you go about young researchers that want to publish with you, and also how you go about young researchers in terms of asking them to be referees.
We all the time look for new referees, and Nature published, I don't remember the year, 2 Swedish, I don't know whether they were PhD students or postdocs that looked in the bias against women, and that really started that. Scientists always thought we are scientific, it doesn't affect us, and it really showed with hard data how much harder women had to work to get their grants funded, and that really prompted a lot of soul searching also at Nature, and very conscious efforts to try be aware that it might be quite easy to be biased against women, and try to consciously increase the number of female referees. And also, with the Black Lives Matter movement, there are certain groups that are not well represented in science, and also sometimes underrepresented in higher positions, in higher impact journals, and in the referees we use. And so there's awareness of that, and also we have, I think it was last year, it was younger, I think it was still, might have been PhD student and postdocs. There was a sort of mentorship program. People could sign up to referee for a Nature journal, and if one in their field popped up, they would be assigned as a referee, and together with other normal referees, and just experienced the process. I myself also always look for young researchers. Yes, you have to give them a chance, and I think it can also be very valuable for a researcher just to see comments of the other referees. Can be very educational, I mean, for everybody involved. So we try to make sure, if we have 3 or 4 referees, that maybe at least one of them is one we know what is likely going to come from them, that they carefully look at it. But also I try to always find at least one referee I'm trying out, just see how they are, whether they are really constructive, whether they put in the time and effort to carefully look at the work. The other question about impact, I don't know, did that answer your question? Yeah, I mean, it's, for me, the job has become really, really busy. Just the work pressures has gone up, and sometimes finding a good referee is, I think that's really the key point to having a paper carefully and fairly evaluated. But it can take a lot of time, especially for editors of Nature, because they have quite a broad range of different topics to cover. Some topics I just really know who to go for or who not to go for, but some papers I need to invest a lot of time. And in that regard, having referee suggestions in a cover letter is really helpful. So even if I don't use one of them, I get exposed to the scientists. And I also always ask, I mean, it's in our standard letter to referees, can you make suggestions? Yeah. So, but we also have to be sure that the comments we get will allow us to make a good, informed decision. And if you have all people, you don't know how good they are as a referee, so try to balance both. And in terms of the high impact, I think it's very, very easy to underestimate how easily one is influenced by subconsciously when making decisions, So with that disclaimer out there, I think my colleagues and me, we all try to look at the paper, we try to look at the scientific findings, and based on that, make a decision. I'm sure sometimes we are somewhat influenced in a way, but we don't know, I don't know anybody who would look up age factor and then decide, yes, it's a very high one, just let's go for the paper, even though it seems not very promising. But yeah.
Yeah, thank you for the insight. I have two quick questions. One is connected to Claudia, because I think it's pretty common that even when you send out a paper for peer review to a PI, actually like junior people are actually refereeing it. So I was wondering, how often does this get disclosed?
How does this get?
Like how often when you get feedback, older PI actually tells you I had help from my junior colleagues?
I medium frequently have people say, oh, I'm happy to do this, review it. Is it fine if my postdoc or PhD students help me with it? And that's absolutely fine. We do expect that referees, if they have input from somebody else, that they tell us. And really ideally, if it's completely another person doing the review, it should really be that person whose name we have on our record as a referee.
As far as I know, it's a common practice
to
collect, send out without disclosing this information. So I was wondering, from your end, how...
I see that sometimes. I mean, I usually... really, it is often people saying, I would like to do that together with this person, my postdoc or my PhD student. Is that fine? But I very, very rarely see a report being delivered and said, oh, this has been done by or with.
And
very
in the
rare.
cases that it gets asked to you, you always, or like most of the time you say, sure, yeah, fine.
No, it's fine, yes. I mean, if confidentiality is honored and they let us know, it's absolutely fine, yes.
And just a quick question. I remember some years ago the double-blind peer review was introduced in Nature. Can you just quickly comment?
Yeah, sorry, we have had quite a lot of, because peer review is just so important, and sorry. Let's see. Yes, Nature at the beginning, it didn't do any peer review, and some really big papers didn't get peer reviewed, and that's a process that Nature continuously is looking at. And this is now a 2017 peer review survey where quite a lot of people, 82% felt it is the process is working, but still a majority thought it would be good to change it maybe and make it better, that was also in preparation of transparent peer review. The double, so you were asking about the double blind?
Yeah, because I heard that the people that actually do double blind peer review get rejected more often. So there is definitely some sort of bias, or maybe...
I think it can vary from field to field. I see very few, it was, I don't know when it was offered as an option. I see very few papers that ask for peer review, and most of them come from Asian countries. I've heard people tell me that they feel there is a bias against Asian scientists. It's whether it is, it will be very, I don't have any information and data to say whether that is justified or not. But if they feel like that and choose double-blind peer review, I can understand that. I have had very few papers accepted. I don't remember actually even one where it was double blind. I think I had one where the authors then changed after the first round of review and said, okay, you can have our name on it. But I know some colleagues have received very good papers and published papers that have undergone double blind peer review.
Thank you.
Hi, I have a question. So we had a recent experience with Nature Metabolism where we submitted a collaboration paper. And, you know, we got 3 reviewers, 2 were great, and then there is always that one that is not great. So I just would like to say that the paper got rejected, but my question follows that, for example, in our line of work in biology, we are trying to characterize how certain protein works, and for this we use screens, yeah, like this gene is upregulating this cohort of genes. So we use genes, we use mass spec, we use RNA-seq, and then based on the results, we filter it. We are applying statistics, we are applying p-values, fold changes, and that filters it to a table of possible hits that we should follow. Yeah?
Yeah.
So a table is usually 20, 30 hits. So out of this, so we've got a table of 30 hits, and out of these hits, we chose one to follow upon. It wasn't the first one, though. It wasn't the second one. It was on the, 12th one. Because we just believed that the function of our genes has something to do with apoptosis, so we actually chose the apoptotic proteins from that list. It was rejected from Nature based on why didn't we follow a more probable first, second, and third hit. Why didn't we try those? Why did we go for hit number 12? And this made us very surprised because we just wanted to ask, like, is there any flexibility for a scientist to actually follow his gut feelings in what he will actually choose to work on? Once he applied really strict scientific criteria to come up with the list, why were we rejected based on that out of 30 hits? We didn't focus on hit number 1, 2, 3, 4, 5. It was just too expensive to do the all 30. And we just chose by gut feeling, imagination, kind of. We didn't have any real scientific support why we chose hit number 12. But we did, and it worked, and it was beautiful. And it just kind of like, is there any space that you leave for scientists just to follow their gut feelings in choosing something? Or you always have to justify everything by scientific means why you actually followed upon something? You mean
you said it was rejected based on that? No, I think, that's...
Based that we didn't follow a sound scientific arguments why we chose hit number 12 and why we didn't first research the first 11 hits from the list. It's just,
if that was a key argument, it must be very frustrating. I do understand that, but maybe that comes back to what you can learn of that is really communication is quite important. I don't know enough about it. You have limited means. I don't know how long it takes to go through all your different hits, but you could just have said limited resources, and you have explained to me why you had a gut feeling, right? So maybe just half a sentence.
Gut feeling to the editor, it's not really. I don't think that they.
Well, you can kind of like, based on our experience, we expected that to be blah blah blah. Just a very hint of indication of why you'd. But it's. I don't know the details. It just seems a bit strange if that was a key reason.
We are going to communicate it. We are trying to. I'm just trying to find the correct words how to pose it. Yeah.
Okay. Thank you very much. I just have 2 questions. The first one was in one of your first slides, you showed that nature is also, trying or actively pushing for a more active discussion forum or like a debate forum for papers. Honestly, if I have a question, I either go to a conference or I contact the authors directly. Maybe I'm naive, but I have never seen like a comment section beneath a paper where it's really a rigorous discussion based on the paper itself. That would be my first question. The second question is, We just had rather bad experiences with a journal where you, after publication, you were given the possibility to include something like slides that explain your paper again. I find this personally maybe the most interesting aspect about a paper. You have the scientific paper, but if I can get the insights, 3-minute or 5-minute presentation of the either first author or corresponding author, describing their research in their own terms, like unbiased from, you know, the entire process, it makes for a much more precise, compact evaluation of the work. So those would be my 2 questions.
We have, I don't know exactly which slide you meant. I mean, I think I was trying to explain that Nature really is a beast with 2 very different hats on. The journalistic part of Nature is really quite big. And so there is also debate. We have commentaries that can sometimes be quite stimulating in different ways. Sometimes it's science, politics, funding. I remember always we once had a commentary about 7 chemical separations that could not quite save the world, but if you could improve them, it would make a huge impact on energy demand, and that was quite stimulating. Not the debate, but so that's all of that. The journalistic section really isn't about discussion of a particular paper. We publish a paper and you can comment on it, but the kind of exchange that you're looking for is not something we offer. We are now starting to have something called research briefs, which is a 1-page piece about a paper that's published, and that is essentially written by the authors, where they do also provide a bit of background behind the scene, why they did the research, and explain in their own words why it is exciting and important. And I think, I mean, those research briefs will vary from paper to paper, and we have had a few of them published. A published paper, you can comment on it online, but it's not really exchange. But this idea of having a little, you know, I think this research brief will give you 1 page, you read through it, it has 1 figure, but having kind of an online video where authors talk about it, I can see the value. It's just, I think in terms of production, it probably is quite involved. But I mean, that's the point I kind of will mention. But I think just practicality is difficult to do.
Just a quick question about the cover letter, and you included, you know, what types of reviewers you could recommend and why they would be relevant, but also sometimes we include people that we'd want to leave out from this process. And the reasons are always unknown. Maybe they don't get along, maybe it's a competitor, whatever. But I imagine there are instances where the field is sufficiently small that many of the people that would be most appropriate to gauge the quality of the publication are within that list. How do you manage something like that?
It's a bit of a headache. It really is difficult. It's very, very difficult. And sometimes you just have to use maybe one of the excluded referees, but keep in mind that they were excluded and try to balance that against the other referees. I mean, it depends on the paper. You know, often papers are experimental, not always, and then you try to find somebody who really knows about the but if it's a very small field and if all the very obvious referees are excluded, yeah, it's quite very, very difficult. And ultimately not helpful, I think, for, you know, I mean, having a paper is just so important for funding, for career, for so many things. But if you have the ideal of that you want to build science and move science along, I'm really somebody who believes in exchange, and, you know, at some point, and if you exchange, you learn so much more. Even if you have to defend your own position, you have to think about it very carefully, and it's something fruitful. And sometimes you reach a point, okay, we just have to disagree, you know, and time will tell. But yeah.
I have a question concerning the fact that you find that, for example, one of the referees is actually the real competitor. He has very similar or almost the same work in his hands as well, and he kind of delays the revision process and publish its own work behind in another journal. How do you see it? How do you handle this situation?
well, we always have several referees. And we try to look at the scientific arguments. Sorry, you meant like when the...
It's delayed.
Yeah, okay.
It's delayed, and in the meantime, and it's obvious. Then you see the name in another journal, and you see, it's exactly this referee who delayed it.
I haven't experienced that. I think it's quite. I don't know. It's probably more likely in the life sciences. Because there just are so many more researchers in groups working on pretty much the same problem. I've had several instances where independently papers were submitted and they were exactly the same, and we published both of them. And occasionally also actually the authors talk to each other. But something like that, I think you would just really, well, not blacklist, but make a note that that a referee is capable of doing that. It's just completely unacceptable and unethical. But you do not know the name, you do not know the name of the referees. It's just like obvious, but you do not know who is your referee. You just see it. There are certain evidences, but you do not know it. So should I, in such a situation, like write to the editor, I'm sorry, I'm kind of almost confident that this is the referee, and can you please have a look at it or deal with it? Or it's better to stay calm and don't deal with it? I have not had many cases like that. I have had authors write to me and making a point like that, but it wasn't valid. And we can never reveal the identity of a referee if he doesn't want to do it, but either in the positive or negative. Occasionally I've then said, it's actually your concerns are not valid because I knew it was maybe a different one, and you can maybe avoid bad relationships developing. It's as an author, I think it probably depends. I don't know. You could get in touch and say, just in a matter of factly, I had this paper, it took so long, was rejected, I've just seen this, I would like to draw attention to that. An editor won't be able to tell you whether that person really was a referee and held it up, but it's information that would be useful to the editor to have for future going forward.
Thank you.
You mentioned that all the referee process was introduced into the Nature relatively late.
Yes.
But there was a tradition in the past that the senior, well-known professor promoted the paper of the younger people. So an example would be, I guess, Sir William Bragg Jr. Wrote a letter to Nature about the paper of Watson and Crick about the structure of DNA. So I think that with the referee process, this tradition was abandoned. When was it?
When was it abandoned?
Yeah.
I think it was a gradual, as far as I know. I haven't really looked into the history of it. I think it was in the 40s, 50s, more rigorous review was slowly being built up. And at that time, there was also Jack, Brimble, the editor of Nature. There were many papers submitted, and there was a large backlog, and he didn't really have a referee system. He stuffed lots of manuscripts that seemed interesting in his pockets. He went to the Athenaeum Club on Pall Mall, where he knew professors, scientists, and he had coffee and just asked them for their opinion. And well, I think it might also be, yeah. I don't know. I think it was a gradual process, and I think it was John Maddox who really took over in '66 and rigorously introduced peer review.
Thanks. So maybe I have a comment as a fellow editor. I mean, I really liked your list of what doesn't work in the rebuttal letters. And your last point is when the author points out that a similar paper of his or her or of someone else was already published in the journal. And there the answer is so simple. You just tell the author, yeah, exactly, because you already published a similar paper, we will not publish this one because we don't want to pollute the literature by another repetition what has been already done, right? So there I felt like this is very easy to handle. And I liked also the cases which work, right? And that's true. I mean, we make mistakes as editors,
yes,
and
yes.
if the authors have a valid point, we do correct our opinions.
Yes.
And the valid points have to be technical and should never be personal, right? I think
yes.
Absolutely. So I think the rules are similar.
Yes, they will be. I mean, at the end of the day, it's about trying to get,
we're trying to do our best.
Yes.
But we make mistakes. Well, thank you very much, Magdalena. This was really great talk and very
pleasure.
discussion.
Thank you.
We will now take a 10-minute break. There's coffee and a little bit of refreshment, and 11:10 we reconvene, and we will have 2 talks of previous winners of the DCA. So DCA 20 and 18, or 18 and 20. Thank you very much. This is great. And,
thank you.
I leave mine here just so that.
Yeah, absolutely.
It's the HDMI, right?
It's the normal HDMI, yeah.
Perfect. And we are using theirs?
This thing, yeah.
Okay.
These things usually work pretty well.
And it's just
Here's the, yeah.
up and down.
Sure.
So sometimes they press something that makes everything disappears. I guess it's it.
So we're continuing with the alumni, and as we will collecting more and more alumni, this event will be longer and longer, so you should be happy we're still in the early stages. And then the winner of 2018 DCA competition, which was in Warsaw, was Głowacki. And yeah, so I don't know if you will now show us how your dream came true or how you completely abandoned it and
plus minus, yeah.
So the plus minus is yours, 30 plus 10.
Thank you so much, Pavel, for the very kind introduction. It's a great pleasure to be here and present to you some of our work. And yes, as Pavel suggested, I will try to tie into how things fit into the actual original dream chemistry proposal. But I will be talking primarily about our work about stimulation of the peripheral and the central nervous system using various optoelectronic devices. So all of the work that we do fits somehow into this new emerging field of bioelectronic medicine. Bioelectronic medicine, as opposed to traditional pharmacological approaches, is that instead of using drugs, chemicals, right, we're actually delivering electrical stimulation somehow to the body. There are many, many various examples of this, everything from cardiac pacemakers, which are, of course, the oldest and most well-developed technology, to things like deep brain stimulation, where delivery of electrical current via implanted electrodes interrupts pathogenic activity in the brain, to many versions of peripheral nerve stimulators, which are intended for various therapeutic applications. So I'll show a couple of those examples, and I'll show how our work ties into that. So broadly, when it comes to stimulation of the nervous system, we can divide approaches into two categories: invasive and non-invasive. In the case of invasive devices, we are talking about something that is actually surgically implanted into the body. Obviously, any surgical procedure carries risk. It can be complicated. However, we can very specifically target an anatomical structure in the body. In non-invasive stimulation, there is no surgical intervention. We are simply delivering somehow electrical stimulation through an intact tissue. This has the obvious advantage of not having surgery, but it's almost always much less specific in terms of what you can locally stimulate. So we'll talk about several types of things that we're doing in both invasive and non-invasive approaches. So just to bring very briefly to you a couple of examples of neural stimulation technologies. One of the most developed today is the deep brain stimulators, which are used for patients who have, for example, Parkinson's disease, where electrical current is injected in the brain to interrupt pathogenic activity which causes tremor. So almost 500,000 patients in the world have this type of stimulator. So this is quite well established. There's several centers in the Czech Republic that perform these implantations. The second, I would say, most common type of surgical intervention is vagus nerve stimulators, VNS. This is what our team works on, let's say, primarily. About 300,000 patients in the world have this, mostly for drug-resistant epilepsy, but also for a number of other different conditions. Cochlear implants, of course, also Pavel is quite familiar with this field. More than 1 million patients in the world have these implants. Analogous to cochlear implants, we have artificial retina stimulators. This is much more experimental. About 2,000 people in the world are in some phase of clinical trials with retinal implants, where electrical current is delivered to the retina in order to give patients, blind patients, some semblance of vision. So implanted neural interfaces broadly fit into two types of categories. One is taking a cardiac pacemaker, like you see here, taking the electrodes and putting them somewhere other than the heart. This makes a lot of sense because cardiac pacemakers are very, very, very well established. So it makes sense that we use this clinically approved technology to simply target a different structure. And that's very much how deep brain stimulation works. The other category of devices involves more sophisticated, smaller implanted probes. These are commonly used for various types of brain-computer interfaces. Nevertheless, this is the current state of the art in terms of clinical applications. In the material science field, which is where we are coming from, the name of the game these days is to make everything as ultra-thin, as flexible, as soft, conformable, stretchable even as possible. So the idea is to make these, I just selected from this review article a couple of pretty pictures. The idea is just to show you that there is a very diverse variety of different extremely conformable and thin and flexible devices that are more biocompatible. This is where the field is going. We're trying to make these devices look a lot less like these hard circuit boards that we're implanting into the body, into something that's looking a lot more like something that's human friendly. So that's the, let's say, motivational starting point of this research presentation. So with that, I'd like to introduce our group at CEITEC in Brno. This is the second largest city in the Czech Republic. Here's our group. Sometimes the sun shines in Brno, but not on the day that we took this photo, unfortunately. Nevertheless, this is a very fun team, and we're very happy. So just for those of you who want a geography reminder, so we are in Prague, and I'm talking about Brno, which is located in Moravia. And this is our center. This is the largest clean room facility in the Czech Republic for manufacturing of micro and nano scaled electronic devices. So when we want to implant something into an experimental animal or into a patient, of course, we have to have very rigorous conditions of reproducibility. And for this reason, we use a clean room facility for manufacturing of our devices. In our group, we work primarily on stimulation technologies. These can be divided into 3 categories. We work on transcutaneous stimulation of peripheral nerves using near-infrared light and implanted devices which absorb that light and convert it into an electronic impulse. We use temporal interference. This means using high-frequency fields, electric fields, which interfere at deep anatomic structures. This is a form of non-invasive stimulation. So I'll show some of these results. We also work on photovoltaic implants for targeting deep brain structures, which are basically a combination of a photovoltaic transducer and some sort of ultra-thin probe. So I won't talk about that too much. But otherwise, we make custom microelectrode arrays. If you want a custom microelectrode array, please talk to me. Maybe we can discuss something. We also make flexible neural recording devices for experimental small animals. So these devices have to be very, very small and flexible, for example, to make interfaces to mouse nerves. And the project related to the DREAM, which I'll talk about at the end, involves the electrical manipulation of oxygen and peroxide levels in physiology. So first, about the issue of powering implants. If you have something in your body, like a cardiac pacemaker, the normal approach is to simply put a battery into it. This is fine, except the fact that you have to somehow replace that battery, which almost always requires a surgical intervention. That's not very nice. So everyone in this field is trying to make things wireless. And some kind of electromagnetic induction is obviously the most clear approach. So most people focus on how to have some kind of sending antenna, receiving antenna. However, there's alternative approaches, for example, using acoustic waves in the form of focused ultrasound. And then there is the much less popular, and we are championing, the idea of using actually optical stimulation, that you can actually get safely relatively large amounts of light through the tissue. So I'll show how we can do that. And the goal of this project of optical stimulation is that we want to replace the traditional stimulation electrode. So, in a traditional stimulation electrode, which was on the, we have some kind of metal electrode that is wired. We have an interconnect, and we apply a biphasic pulse to it. So we apply a negative charge pulse followed by a positive charge pulse in order for there to be no net injection of charge into the body. This negative phase will cause the cell to depolarize and fire an action potential. What we are trying to do is how to replace this wired protocol using only optical power. So in optical power, we cannot have negative light, right? We can only have light going on and off. So we have some kind of optical power, and we want to have a photoelectrode which has no wire and is powered by these light pulses. So first of all, we have to discuss which kind of light we're talking about. The kind of light that we're using is what is the deep red phototherapeutic window. This is a set of wavelengths between about 630 nanometers to about 800 nanometers. This is where the various biopigments like hemoglobin and so on are not absorbing light. And we're not too far in the near infrared where water starts absorbing, because then we get heating, and that's obviously not good. So we have to stay in this deep red window. So you, all of us, were super transparent to this deep red wavelengths of light. You can convince yourself. Here my colleague has a 660 nanometer LED. It's a 3-watt LED that we bought on Amazon, and you can see how nicely the light is shining through her hand. And in this case, it's powering a drug pump device. But the point is that we can get red light, high powers of red light, let's say several tens of milliwatts per centimeter squared, to a depth of about 15 millimeters below the skin. This also includes to the skull. The skull is quite transparent. It's, to these wavelengths, the skull is very easy to get light through, both in humans and experimental animals. So that's how we get light in. How do we convert that light into an electrical impulse? Well, we use this very old, tried and true approach. It's this beautiful paper. It's my favorite paper ever. It's 1.5 pages long, and every sentence is as correct today as it was back in 1986. And this is Ching Tang's idea of a 2-layer organic photovoltaic cell, where he used a bilayer of evaporated organic pigments. These are very, very, very well-known commercial pigments, which are super cheap and extremely stable and are approved for, they're very safe. They're used in cosmetics, they're used in paints, they are dyes that you come into contact with every day. So we really like this approach of using these types of absorbers. And what we did with these absorbers is we created something that we call the organic electrolytic photocapacitor. And the electrolytic photocapacitor works like this. We have a PN junction which absorbs impulses of light. When it absorbs impulses of light, it will generate electronic charge carriers, electrons and holes. The electrons will pile up at this interface with electrolyte. The holes will be driven into a return electrode, which is necessarily of larger area and extended around the PN junction in order to complete the electronic circuit. So when electrons go here and holes go here, in electrolyte, in your body, you have no free electrons and holes, unless you put, the ammonia and stuff, but we're not gonna go there, right? We have no free electronic charge carriers, but we have ions. So these ions will move in the electrolytic solution to balance this electronic charge, and that movement of ionic current can be used to generate electric fields in solution. And if we have, this is just a picture of an idealized cell membrane, if we have a cell membrane nearby of this PN junction, you notice minus is here. On the other side, we will get plus. We will get capacitive coupling. We will get depolarization of the cell membrane. And this concept works. So very briefly, these are intracellular recordings. These are patch clamp recordings inside of singular cells. And what you can see is that when we shine, for in this case, a 10 millisecond impulse of light, we see that when the light turns on, we see a large negative voltage peak. When the light turns off, we have a positive peak. There is our biphasic charge balanced delivery. That's exactly what we were after. That's how we convert a square pulse of light into a biphasic ionic current pulse. So this can be used to stimulate cells. In our first experiments with cultured neurons, these are hippocampal neurons. These were cortical neurons in this case. And what we did calcium imaging. When you see we shine a train of impulses, all of the cells in the field of view fire an action potential at the same time. So this was our first indication of the fact that this concept worked for depolarization and stimulation of neurons, as well as some indication of biocompatibility. This was published back in 2018, 2019, and now we have followed up with this work in vivo. So we have translated these photopixels onto ultra-thin plastic cups. So we make these cuffs out of Parylene C. This is a biocompatible plastic. The cuffs are about 5 microns thick. So they're very, very thin pieces of plastic. We wrap them around a peripheral nerve. In this case, we use the sciatic nerve of a rat as a model. And then what we're doing is we surgically implant this device, and then we are shining impulses of light through the intact tissue interface in order to deliver these charge-balanced biphasic pulses and stimulate the sciatic nerve. The sciatic nerve is a very convenient model because in the sciatic nerve you can record muscle activity to prove that you're delivering stimulation. You can also see visual movement of the animal. So in this case, this is an acute experiment before we close the animal. And we see that once we wrap this device around the nerve, we are delivering impulses of light between 200 to 1,000 microseconds is the length of the light impulse. My colleague is acting as an optical shutter. And you can see that when he's blocking the light, nothing. When the light hits the implant, you see that the rat is kicking. So this was our very first indication that this indeed works. And this type of acute experiment on an anesthetized animal is fine to prove that we're going in the right direction. But the real challenge is how to design an implant that's easy to surgically manipulate, and it's going to be stable over time. We want to fix this in position and not have it move over a long period of time in a freely moving animal. So for this reason, we've developed this chronic design of a zip tie. We were inspired by a simple cable zip tie, where here's the PN photo pixel that's actually generating the stimulation. The rest of this plastic is coated with golden ITO, so it's conductive. That's the return electrode. And then we have these reinforced metal teeth and a reinforced metal locking loop. So what we can do is we can pass the ribbon through the loop and have the teeth lock. And this is for size, this is finger. You see that this is a few millimeters the size of this device. This takes just a few minutes to implant. It's very, very easy. The surgeons were very happy. So they were able to do this very quickly. So this is how it works. We isolate the nerve, we put the implant around it, we pass it through the loop, we close the animal, we're done. And then we can shine light through the tissue interface, and we can observe activation. So, video. So here's a video. This is 100 days after implantation. It's on my computer, it's playing, but on the screen it's not playing. Oh, it is? Okay, I guess for stupid Zoom meetings, I always slow it down because of the frame rate. So here's the implant site, and then every time you see a red light coming, you should see him kick. And these duct-taped electrodes are EMG electrodes. Okay. But you saw something? Okay, good. Well, it works. In any case, we did those experiments for 100 days. We have the same types of devices can be implanted onto the cortical surface to do cortical stimulation. So in this case, we've developed devices for photocapacitive stimulation of the motor cortex in experimental animals. And in this simple experiment, we have implanted both hemispheres of the somatosensory cortex, and we can shine light, and we can observe, depending on which side we shine on, we can observe whisker motion on either side of the mouse. This is good proof that we are delivering that we are able to do transcranial photocapacitive stimulation through the skull. Right? So this is the device is implanted on the surface of the brain. The skull is replaced on top. So the next thing I want to talk about is going completely, these are new results that I'm very happy about. We submitted this paper yesterday, or this manuscript yesterday. So I'm very happy. It'll go on bioRxiv too, so you can see it. But it's our approach to completely non-invasive stimulation by using interference of high-frequency electrical fields. This idea was first proposed by Neil Grossman in 2017, so it's a relatively new idea. And it's based on the phenomenon that you can have two pairs of electrodes, okay? One operating at one frequency and the other operating at a similar frequency, but with a small frequency offset. So for example, you can imagine 1,000 hertz and 1,010 hertz. What's going to happen is that you're going to have interference patterns. And these interference patterns will have an envelope frequency, so an amplitude modulated envelope, at the offset frequency. So we will have an amplitude modulated envelope that is oscillating at, for example, 10 hertz or 50 hertz, whatever the offset is. And the reason that this works is because if you use very high frequency fields, neurons are transparent to those frequencies. Neurons cannot react very fast. So if you apply more than 1,000 hertz, the neuron is just looking at you. It cannot activate fast enough. So we use relatively high, in our experiments, we actually use 3,000 hertz. So the first assumption is that high frequency E fields do not generate stimulation. And the second assumption is that we can have some area of overlap where we will have an amplitude modulated envelope at an offset frequency that is a stimulating frequency. So something on the order of 1 hertz to 50 hertz. And we have applied this to do non-invasive stimulation of peripheral nerves. So in this experiment, what we've done, it's again the stimulation of sciatic nerve. It's a very well-established model. And what we're doing is, so clinically, people use transcutaneous stimulation all the time. It's very controversial. It's very inefficient. I mean, we can debate about this, but the papers in the literature are a complete mess. Some people show efficacy in the clinic. Some people say it completely doesn't work. Our experiments show that most of these experiments really don't actually deliver stimulation down to the depth of the nerve. In any case, what we did is we used these 4 electrodes with 2 different frequencies in order to have an interference at the site of the actual nerve. So in this case, we used 3,000 hertz and 3,000 hertz plus some frequency offset. And in the next slide, okay, good. So here's the offset of 0.5 hertz. So you see he's kicking once every 2 seconds. Now we have an offset of 1 hertz. He's going to kick every second. We're applying 350 microamperes of current. So this is 6 times lower than what we needed in order to get a response using the conventional method. 6 times. Now, twice a second, he's going to be kicking. Now he's going to kick faster. So you see that really this interference pattern, you see this beat frequency actually delivering the stimulation to the leg. Now he's going to kick 4 times a second. The convenience of this method is that, I mean, in this experiment, we used simple gold pins. But what is smarter to do is to actually have a flexible grid of electrodes, which you can roughly put over the anatomical site. And then you can automate cycling between electrode pairs in order to do automated targeting. This is very, 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 very convenient. So this works as well. You can see the guy is kicking. OK, and now in the last 5 minutes, now for something completely different. This was shown at least once yesterday. And that is the connection to the dream chemistry. So I found my presentation from 2018. This was the first slide. So at that time, I was in Linköping, Sweden. And the idea was to make abundant organic catalysts for peroxide clean energy cycle, for energy applications. And the concept was that we could take atmospheric oxygen, reduce it selectively to hydrogen peroxide as a metastable high-energy product, and store it as liquid fuel. And then the concept was that, hold on, is the key, yeah, okay, that we generate peroxide. This is an uphill process. We store it. We can store it as a liquid, and then we can convert it back to electrical energy using fuel cells. And the key to this will be organic catalysts, right? So indeed, we have been working on those organic catalysts. We've been optimizing this concept of oxygen reduction via 2 electrons selectively to hydrogen peroxide, but we have not been doing it for energy, I admit. Other people have. So a lot of papers come out on this. So I'm very happy that this field has been moving, but our interest is biology. And the thing is that hydrogen peroxide in biology has many very interesting functions. So at high concentrations, obviously, hydrogen peroxide will kill everything, right? This is bleach. This is going to completely kill cells, eukaryotic and prokaryotic cells. But at lower concentrations, peroxide is important in many fundamental signaling pathways. It has many roles in regulation of ion channel function, and so on. So this is something quite interesting. And one thing that we focused on is in our group, we have quite some experience with kV channels. These are potassium channels, voltage-gated channels. And there's this paper from 2006 by Nikita Gamper, where he found that if you add peroxide, these kV7 channels are modified, oxidatively modified by the peroxide, and they start leaking out potassium. And this is very important for actually down-regulating pathological neuronal excitability. So some forms of epilepsy are actually caused because of these channels not working in humans. So what we did is we used our favorite model, Xenopus oocytes, to overexpress these channels from this 2006 paper. And we tested that if we add peroxide, we get the very similar response curve like what Nikita Gamper published in 2006. And then what we did is we developed a pixel, which is going to use this organic technology that was the DREAM. So we used the organic catalyst from the DREAM in order to create an electrode that's going to specifically dose the peroxide to this single cell. And around that electrode, we're going to put a guard electrode, which is going to neutralize that peroxide. So we have like a peroxide fountain, which can stimulate individual cells. So for example, this is the actual profile of peroxide concentration that forms. Over the course of several minutes, you can see that peroxide concentration grows. Meanwhile, we're consuming oxygen, so oxygen is going down. We're using up oxygen and creating peroxide. We measure this using these amperometric probes. And what we did successfully is we actually had this oocyte in the center of this pixel. Here is the perfusion curve. So we are perfusing peroxide in. It's a controlled experiment. We're perfusing peroxide in. We see the increase in potassium current. So we see potassium current going up, 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 up. And in these curves, we're not adding peroxide. We're just running this pixel, running low-level DC current between P.PSS and palladium. And we see a very similar curve. We see this increase of potassium. So we want to use this as both a research technique, but also possibly as a therapeutic approach to use implanted electrodes to dose controlled amounts of peroxide in order to stimulate areas of the brain which are overexcitable and have a defect in these types of M channels. So sorry to rush through that a little bit, but we have some time, hopefully. So I'd like to, of course, thank our group in Brno, my former group at Linköping University, a few key collaborators that were really important in the work that I showed. I thank you for your attention. If you want to join our team in Brno, please write to me. We're very interested, especially for students and the funding, the city of Brno and the ERC. Thank you.
Thank you very much, Eric, for a great talk. And it's nice to see that the dreams are developing and moving into different directions, as they should, right?
Yeah.
You wake up in the morning and get this wake feeling. That was a nice dream, but we carry on into life, and
yeah,
part makes it up, part doesn't. That's perfect as it should be. Okay, questions, comments? So how far are you with these electrodes from mice to people?
That's a good question. The next stop is pigs. So I mean, I have somewhere here so the goal right now, the main funding that we have is to replace the classic cardio stimulator for vagus nerve stimulation using this implant, because a lot of patients, they only require a couple of minutes of stimulation per day, and they're dosing the stimulation themselves. So what they do is they actually activate their pacemaker by hand, which is kind of stupid because this surgical procedure is very, very, very invasive and very involved. So what we want to do is to do this by this minimal cuff implant, but we have to do this in pigs first. So this works in mice, it works in rats for vagus, but we need to go to something bigger and track it for a long period of time, because the longest experiment we've done is 100 days.
Pigs are like almost humans for this.
Almost.
Okay.
Yes. Next stop, pigs.
Yeah. Jarad.
Oh, sorry, it's in Czech.
Thanks for the great talk. I was curious for the red light transmission. You said it's very transmissible through the skull. Can you think about using the same type of approach for like deep brain stimulation for Parkinson's treatment? Do you think that's possible, where you might have like more selectivity rather than like electrodes that once they're implanted you can't really move? If you could control like what's stimulated via where you shine the light, if you'd have better resolution and maybe more efficacy.
Yeah, I think so. We have a technological approach to that. However, the problem with deep brain stimulation is not the power transfer, so to say. It's the microelectrodes delivering stimulation locally to a very small area, the size of a grain of rice, right? So I think that our optical approach, yes, we can make it wireless. We can put something on your skull underneath your skin and have a very small craniotomy. So that's what we can offer. We can offer a more minimally invasive solution, but I have to say that our approach is not solving the fundamental problem. Okay, this example is for the hippocampus, but for deep brain stimulation, it's the same issue. I mean, it's very difficult. I don't think our approach is fundamentally somehow solving the problem of deep brain stimulation. Just easier surgically. Yeah.
Okay. Johannes?
Yeah, also thinking about this stream, I mean, this technology seems very compatible with these other syringe injectable electrodes. Like maybe are you thinking about using this to kind of inject minimal invasively and then kind of form the mesh?
Yeah, I'm familiar with the mesh work that you're talking about for the brain, right? I mean, yeah, we have not really been thinking about this, to be honest. I mean, our approach was more about like making a very small surgical incision and having something which you can really put around the nerve that you can size and have it there in a very reliable way. That was more of our approach, like not injectable, but surgically minimally invasive and very precise, because clinically that's what.
No, clinically it would not make sense, probably just experimentally, and if it works or not.
It could, in principle, yeah. I mean, you can. The advantage of our thin film technology is you can put it on anything. I mean, we put it on plastic, right? It's a low temperature process, so you can evaporate it on whatever you want. So cool. It's possible.
Okay. There are no more questions. Thanks a lot again, Eric. Good to see you here. And we will continue with Claudia Bonfio, the winner of the Dream Chemistry Award 2020. And I should say, like, because this was a purely online event due to the pandemics, and I saw when Claudia won, she had this tears in her eyes, and it was not clear if it was tears of joy or tears of sorrow that she couldn't be there personally. So yeah, I mean, here she is, and we're very happy to have you in vivo now, and yeah, looking forward to your talk.
Okay. Thanks a lot for the invitation this year. And I just want to spend a few words, because I know that some of the finalists are leaving during the talk. I just want to spend a few words saying that it was a pleasure to meet you, and congratulations for being here among the 5/6 finalists, and to Jarad for winning the award this year. So as Pavel just mentioned, it's very different, and it's really nice for me to be here this year, because last year was virtual. So this is a picture of how it looked the moment I learned I was the awardee last year. Yeah, and I remember that when the announcement was made, they said something like, I can already see her smiling, and I wasn't smiling, so I was like, oh, okay, that's not me, and then it was like, really, it's me? So this is a picture of the moment in which I was awarded, and this is a picture of when I received the award, and you can see that my cat really enjoyed the statue. Last year, probably she wouldn't enjoy the one from this year, because she wouldn't be able to scratch herself on that. But this is what happened last year, so I'm really happy to be here with you. And I also took some of the slides from my talk last year, as Eric just did. And so this is one of the first slides of my presentation last year, and it introduces what I've been working on in the past years, and also what I'm planning on doing, which is focusing on how life started on our planet. And Albert Eschenmoser said that the origin of life cannot be discovered. We might not be able to go back in time. Definitely we don't have the technology and knowledge yet to go back in time. But what we can do is try to reinvent in the lab, or theoretically, what might have happened about 4 billion years ago. And so when I decided to apply for the Dream Chemistry Award last year, I started thinking about what my dream was. And so what I dreamt about, and I still dream about, is understanding how cells communicate, and specifically how cells started to communicate when they first arose on early Earth. And this is particularly timing because today there's a Nobel lecture for the Nobel Prize in Medicine that was about that is about receptors, thermal and pain receptors, and cellular communication. We all know that is mostly based on receptors that are complex machinery that are placed on our cells that can transmit chemical messages between different cells. And so this is what I was interested in, and this is what I'm still interested in and hope to resolve in some time. And so how do we go about understanding how cells communicate and how that started? Well, we need to do quite a few steps back. So when we think about what a modern cell is, we can sort of summarize that as a combination of different building blocks that can drive, power, and protect the chemical reactions that occur inside our cells. And these three building blocks, these three main ingredients, are proteins, nucleic acids, and membranes. And so when we think about how these might have started, how a cell would have looked like on early Earth, it is quite likely that they looked exactly the same, just much more simpler systems were forming them. So primitive versions of nucleic acids, proteins, and membranes. So I've talked about last year during my presentation of the advancements in the field, and I talked about how I, together with a lot of other people, tried to understand how all the different building blocks of life might have formed on early Earth. So how nucleic acids, starting from nucleotides, amino acids, building blocks of proteins, lipids, metal cofactors might have formed on early Earth. And then I've also mentioned a bit about the most recent work at the time I was focusing on, which was starting to combine these building blocks, because these building blocks are nothing if they are kept apart. They need to be combined together in order to form what we consider today a living system. And so if we think about, if we go back to the image of the primitive cell that I showed you, of course, a cell is based on combination and interaction between all its building blocks, but this is not a completely independent system. As I was mentioning before, there's interaction that goes on between different cells, modern or primitive cells, with the environment around these primitive cells and with other cells as well. So this is how you would draw a primitive cell. You would show the influx of nutrients, substrates of reactions from the outside. You would imagine that they can be used inside in different chemical reactions and machineries, and then there would be waste that gets released. This is how we draw it. This is not what we do in the lab. So when we try to make a primitive cell in the lab, what we actually do is we put everything already inside. All our substrates for our chemical reactions are already inside our primitive cell. And we don't really care about the waste because we are just interested or focusing right now on having the chemical reaction working inside the primitive cell. And so we are not yet thinking about the next step. And so the problem here is that if you think about the next step, so if you think about, for example, having a chemical reaction producing a useful product in the, inside our primitive cell, then you have to think about the fact that if your chemical reaction is really efficient, you're going to accumulate a lot of product. And at some point, the reaction just will stop working. Or it could be that you are producing something that is useful and that can be used as a substrate in another primitive cell. How do you go about that? You have your product trapped inside. And so the question I decided to answer in my lockdown project or transition project between the end of my postdoc and the beginning of my independent position was how can we find a way to mix the content of different primitive cells so that we can move to the next step, so that we can look at different reactions occurring one after the other. So the kind of system that I decided to focus on was a very simple system. So at the beginning, I didn't have any primitive, any content inside the primitive cell. I was just looking at what primitive cells intended as membranes, so intended as liposomes, empty liposomes would behave. And the kind of molecule that I was using to make liposomes are fatty acids. This is a decanoic acid molecule, and this is because these are considered among the most prebiotic lipids, amphiphiles present on early Earth. And so basically what I did was just looking at liposomes made of fatty acids. And the reason is because my PhD supervisor, with his postdoc supervisor, so Sherif Mensi and Jack Shostak, published a paper about 10 years ago about the thermal stability / instability of primitive cells based on fatty acids. And what they saw was that if you take a liposome solution of fatty acids and you heat them, what you observe is that the content of these primitive cells gets completely released at a certain temperature. And this temperature and this phenomenon happens at different temperatures based on the different size of the fatty acid that they looked at. So shorter fatty acids release their content at lower temperature compared to longer fatty acids. And also depends on the size of the content. So smaller contents, of course, gets released more efficiently at lower temperatures. So that was, let's say, the first important study about thermal stability of primitive cells. The problem was that we didn't know exactly why that was happening. We didn't know at the time why thermal stability was played such an important role and why this phenomenon was happening. And so we couldn't use it yet. So I was curious about this, and I decided to reproduce their results. And what I did was using two different techniques. So UV-Vis absorbance, everyone knows it, everyone learns it at the beginning of their chemistry degree, and fluorescence. So what I did was taking a solution of lipid membranes made of fatty acids, heat them, and record the turbidity of the solution and how the turbidity would change. And this is the gray line that you are seeing here. So what you can see is that if you start from a solution of liposomes, at some point, and you heat that, at some point you have a very strong increase in turbidity. And we decided to do the same experiment looking at that with fluorescence. And in this case, what we did was embed in the lipid bilayer a molecule that is sensitive to to its environment, so to the phase, the state of the molecules that are around it. And what you can see here is that more or less at the same temperature, the fluorescence of this molecule changes drastically because its environment changes. So again, we were not sure what was happening and why it was happening. It was happening at the same temperatures that were observed in the previous paper that I mentioned. So the first thing we decided to do was look at modeling, try to understand how that turbidity change would be explained. And what we saw was that when you start from a liposome solution made of liposome that only have one bilayer, which are unilamellar vesicles, what you have is a very low turbidity, especially if they are very small. When you start to increase the number of layers that you have in your primitive cells, in your liposome, you have a slight increase in turbidity. But definitely that was not sufficient to explain the very strong increase in turbidity that we observed. And that could only be explained by very large lipid structures that were present in solution. And so what we decided to do was try to understand exactly what was happening. And so what we did was taking a solution of lipid membranes that are fluorescently stained and heat them. And what you can see here is that the lipid membranes at some point at very high temperature start to form very large oil droplets. This happens at relatively high temperature. These oil droplets tend to coalesce, they tend to form even larger oil droplets, and this continues to happen until you start to decrease the temperature. And so when you start to decrease the temperature, these oil droplets become relatively unstable, and what happens is that at the very end, when you get back to room temperature, you have membranes budding from the surface of the oil droplets. So I'll just show you a few pictures of this phenomenon. These are cryo-EM and confocal microscopy pictures of what you've just seen. Starting point, we have unilamellar, very small liposomes that cannot be seen by confocal microscopy. At the end of the thermal cycle, we have very large multilamellar systems that now can be seen with confocal microscopy. If we look at what happens during the whole video, these are pictures from the video, you can see how lipid vesicles, MA stands for myristoylic acid, which is the fatty acid we used. You can see how lipid vesicles look and how oil droplets look at high temperature. When we go back, what you can see is that there are membranes that are now forming from the surface. These are nicer pictures of the same phenomenon where you can see the oil droplets that is more like an onion-like structure, and you can see new liposomes that are forming from its surface. So basically what we could see was that at room temperature we had liposomes, at high temperature we had oil droplets. We weren't sure about why that was happening. And so we went back in literature and found that the ternary diagram, phase diagrams for fatty acids that say that when the pH of a solution of fatty acids is very low, fatty acids would be oil droplets. If you have a very high pH, fatty acids would assemble into micelles. At neutral pH, fatty acids would form liposomes. So what this diagram tells us is that if you change the pH of a solution, you can observe a phase transition from oil droplets to lipid vesicles to micelles. What we were doing, though, was not changing the pH, was changing the temperature. And so what we decided to look at was whether the pH was changing in solution. And what we observed was that in the buffer that we were using to prepare our liposomes, which is Tris buffer, the pH would go, when the solution changes temperature, the pH would go from pH 8 to pH about 6.5 within 60 degrees. So from 20 degrees to 80 degrees, you go from pH 8 to pH 6.5. This does not happen with other buffers. And so what we next decided to do, this is a solution just with the buffer, there are no liposomes in here. What we decided to do was introduce the liposomes, and what you can see is the same technique that I showed you that I mentioned before with fluorescence. You can see this is the same curve I've showed you before, where you have liposomes in Tris buffer, and you can see that the fluorescence changes at a certain temperature. This doesn't happen in PBS, in phosphate buffer, this doesn't happen. And the reason is that the pKa of Tris is very sensitive to temperature, the pKa of phosphate is not as sensitive to temperature, which is something that every biologist would know. It's something that I ignored, and luckily enough, people before us ignored as well, so that we could publish this. But these are some images that show exactly the same. So starting point, very, very small liposomes. We couldn't see them with confocal microscopy. High temperature, nothing happens in phosphate buffer. Oil droplets form in Tris buffer. And then at the very end, when we have, again, room temperature, same situation as before in phosphate buffer, bigger vesicles in Tris buffer. So we tried other buffers, and you can see that changing the buffer changes also the temperature at which this phase transition occurs. And so this proves that despite what was thought until last year, fatty acid membranes are not necessarily thermally unstable. It depends on the buffer that you use. And so in an origin of life context, it depends a lot on the molecules that you have around. And so what we decided to do was explore a bit how much we could change this phase transition. So if you start from a different pH, you can tune the phase transition at a different temperature, to the point that you can even not have at all the phase transition if you start from a sufficiently high pH, so that you never get to the point in which membranes become oil droplets. Or when you have a too high pH, you actually form micelles at the very beginning, and then you have the phase transition to lipid vesicles. And this phase transition temperature could be changed, could be tuned, modulated by addition of basically any molecule that you have in solution, which is quite relevant because it shows that when we look at single building blocks in an origin of life context or not, we tend to assume that what we are observing is very general. But this shows that as soon as you start adding some components in solution, the behavior that you thought was general might not be general at all. To the point that, for example, what we observe with decanoic acid membranes is that the phase transition occurs when you have nothing in solution around 65 degrees, and when you have a positively charged peptide, the phase transition happens at 30 degrees, which is almost room temperature. So if I go back to the big question I had at the beginning, how can we use this to mix the content of primitive cells? Well, what we decided to do was introduce some content. So what we did was we prepared liposomes that had some fluorescent content. We exposed them to the thermal cycle. And what we observed was that at the end of the thermal cycle, we had a small amount of liposomes that still had the fluorescent content inside, while most of the fluorescent molecule was released. We weren't sure whether this result was due to the fact that some liposomes survived and some didn't. So what we decided to do was the exact opposite experiment. You have only fluorescent molecules outside the liposome. You heat them and you cool them down. Again, we had some liposomes with the fluorescent content inside, which suggested that some of the content that gets released during the thermal cycle, during the heating ramp, gets re-encapsulated during the formation of new membranes. So we decided to move to the next step and see if we could actually mix the content from different primitive cells, from different liposomes. So here we have two populations that had different content. We mixed them together, we exposed them to the thermal cycle. We now have a mixed content inside our new daughter primitive cells. The same happens with the composition of the lipid membranes. So if we start from two populations of lipid membranes made of different lipids, and you mix them and you expose them to the thermal cycle, again, you can mix the composition, the lipids that were forming the two different primitive cells into these new daughter cells. And so the last thing that we decided to do was try to see if this could actually be useful for something. So we decided to use an RNA aptamer, and we decided to try to reconstitute the RNA aptamer. And what we did basically was we divided into two parts the aptamer. We encapsulated each part in two different populations of primitive cells, combine them, so mix them, expose them to the thermal cycle, and only if the content gets mixed and re-encapsulated inside the primitive cell, what you have is the formation of the aptamer that in the presence of the fluorogen becomes fluorescent. And this is exactly what we observed. You can see here we have microscopy images that show that we had a certain amount of the aptamer encapsulated inside the primitive cell, the daughter primitive cells, and active, so fluorescent. So concluding, what we observed was that thermal fluctuations can enable the reshuffling, the mixing of primitive cell content and membrane composition, and you can achieve that by using reversible and tunable lipid phase transition that can be modulated depending on what you have in solution. This allows for the release and re-encapsulation of the primitive content and gives rise to a new cohort of daughter protocells that now can be potentially more advanced compared to their parent protocells. So this is what I described to you. We are trying to make this drawing a bit more real, a bit more concrete. So what's the next challenge that connects back to the dream chemistry proposal that I discussed last year? Well, what I think we need to think about, and again it connects back to not only origin of life, but also what the Nobel Prize this year for medicine was given for, is how different primitive cells, when in general how different liposomes with different content can interact with one another, how they can exchange molecules, how they can catalyze reactions in synchronous. So with this, I would like to thank you all for your attention, all of my collaborators. We have my PhD supervisor, my postdoc supervisor, my co-supervisors during my PhD, and these are all the people that contributed to the work that I've just shown you. And so if you know anyone that would like to move to Strasbourg to join my new group, or if you want to get in touch for any reason and collaboration, feel free to do that. And so thank you very much again for your attention.
Thank you very much, Claudia. It's nice to see how things are developing. It's only 1 year, but some progress is nice to see. Okay, questions, comments? Ahmed.
It's a really nice talk and really cool work. Immediately after I saw your graph with the different dipeptides, it looked like that dropped the temperature where the budding happened. The first thing that I thought of was how could you turn that into a signal where maybe you generate that inside the lipids, that causes them to break apart, then you dilute it out and build it up again. Have you considered trying to turn this into a system where you maintain or propagate information in a way like that?
So that's definitely something we are considering. We haven't yet started work in that direction, also because we are trying to understand, we are actually trying to understand all of this data, because there are quite, as always, you publish results and then you have so many other things that come from there that you have to explain. So, for example, here I've put the results with dipeptides. It's very interesting. We've noted that if you have single amino acids, the effect is exactly the opposite. So it looks like that single amino acids stabilize the lipid membranes, while dipeptides don't. So other than explaining why this happens, something that we are thinking about is, for example, looking at peptide synthesis in the presence of liposomes so that you can tune in two different directions, let's say, the stability of liposomes. And this could be also interesting in terms of applications of liposomes that can be destroyed or release their content and reformed. Something else that we are looking at is it looks like there's almost no effect, no difference between the effect of AMP and ATP, which have very different charges. This is something else that we are trying to understand also in terms of their effect on the permeability of the lipid membranes. So definitely the direction we want to go towards is what you were discussing, and that's also something that we've tried to address at the very first step, the sort of proof of concept, reconstituting the RNA aptamer. So the idea now is to try to understand what's going on so that we can move towards that. So, yeah.
Okay, do we have more questions? I remember from last year's competition, I hope I remember it well, what I liked in your talk was this proposal to study the interaction between artificial cells and real cells. What's going on there?
So it's still the idea. I mean, definitely, that's the ultimate goal. I was saying these days that when I wrote the dream chemistry proposal last year, I thought it was going to be like a 5 years dream. Now I realize that it will take maybe 15 or 20 years to get there. So there's quite a lot of research that has been already done in terms of communication between artificial cells and real cells. And my PhD supervisor has published quite a few papers in that direction. Of course, those systems all involve very advanced biological machinery, and I'd say that we are still a bit far in terms of chemistry to get from simple chemical building blocks to something like that. But definitely that's the direction. So hopefully by understanding a bit more how we can combine different primitive cells or different models, then we can move towards interaction with living systems.
Thank you. Okay, so if we have no more questions, thank you and thank all the speakers. We're done with the scientific program, but we would be shameful hosts if we would end like this. So there is still lunch for the active participants, like yesterday, same place? Yes. On the 5th floor, so please refresh yourself, and then you're free to roam in Prague, return home, whatever you desire, and thank you very much again.